Hey, welcome to Let's Get to the Marks. This is the A-level chemistry walkthrough for Paper 1, Inorganic and Physical Chemistry 2024. Oh, my days, a whopping 9 questions to get through, but you've got 2 hours. What I suggest is at the start of each question, you press pause on the video, you have a go at the question with a pen, paper. You're going to need a calculator. It's A-level chemistry, folks. Don't expect to do a walkthrough without a calculator. Make it active. If you don't want to write stuff down, just make sure you pause each go and try to work out what the answers are in your head. Then you unpause and watch the explanation. All right, guys, let's get into it. So the question is about atomic structure. 1.1. In 1897, J.J. Thomson discovered the electron. He suggested that atoms were positively charged spheres with electrons embedded within them. Figure 1 represents an atom of Thomson's model. So we have this sphere, like a football, of positive charge with electrons embedded within. Suggest the identity of this atom. Give two differences between the modern model of an atom and the Thomson model of an atom. So we need to suggest the identity of this atom. Adam? Suggest the identity of Adam. He was from Somerset. No, we need to suggest the identity of this atom. And of course, there's 5 electrons. So we just need to go to the periodic table. We know that if there's 5 electrons, there's likely to be 5 protons. So we count the atomic number 1, 2, 3, 4, 5. If it's a neutral atom, and it did say atom, then this is going to be boron because it will have 5 protons and 5 electrons. Let's go back. Zing, zang, zong. Okay, so the identity of this atom is boron. Hopefully you got that right, guys. Oh my good gosh, it's taking me forever. So there we go, boron. Right, what is the difference between this model and the current model of an atom? Right, well, the electrons should be in shells. So one difference, electrons are now in shells or energy levels or orbitals. And what's another one? Differences between the modern atom and Thomson's model. The positive charge is caused by, by protons in the nucleus. Now, they did know about electrons. Thomson was aware of electrons, which is why he had a sphere of positive charge and electrons, but they hadn't discovered the proton yet. That came later. The end of this model, of course, you had the alpha particle gold leaf experiment with Rutherford and his crew, and they actually worked out that there was positive charge was concentrated in a dense nucleus. But it was later on things like the neutron with Chadwick was discovered and the proton was discovered before that. But yeah, okay, that's going to get you all 3 marks. So boron, electrons in shells, positive charges caused by protons in the nucleus. Okay, we now know that the mass is made of neutrons and protons in the nucleus. We could have said that as well. Okay, and we could have given the idea of electron orbitals, electrons at different distances, that kind of thing. Right, 1.2. Tellurium has a relative atomic mass of 127.6. Iodine has a relative atomic mass of 126.9. Very close, those. Define relative atomic mass. Suggests one property of tellurium that justifies its position before iodine in the modern periodic table. It's worth 3 marks. So we need the definition, first of all, of relative atomic mass. You just have to learn this. If you try to get your head around understanding it, it can be a pain in the butt. Why don't you pause the video, have a go at these questions, and then I'll go through the 3 marks. All right, I'm going to go through the answers. So there are many, many different definitions for the relative atomic mass. You just need to pick your favorite one that makes sense to you. So the relative atomic mass, I go for the mean mass. You can use the word average of an element's atoms. So, or the isotopes of an element, or all the different versions of atoms, basically isotopes of the element. And that is compared to 1/12 the mass of carbon-12. So compared to 1/12 the mass of carbon-12. Okay, so that is my definition, and that will get you a mark. Now, the justification here, it says suggest one property that justifies its position before why tellurium comes before iodine in the periodic table. Right, where's iodine? Here we go, group 7. Let's go down to iodine. Why would you put tellurium before iodine? There's quite a lot of reasons, really, isn't there? I mean, look at the atomic number. The atomic numbers increase from left to right by 1 going across the period. And we can see that tellurium has 52 protons, iodine has 53. So there's one reason why tellurium shouldn't be in the same group as iodine, and iodine should be further from it. Also, iodine is in group 7, so therefore has 7 electrons in the outer shell, supposedly, and tellurium is in group 6, so 6 valence electrons. So again, those are reasons why tellurium should be there and iodine should be there. So we can look at the atomic number, so the number of protons, or we can look at the number of electrons in the outer shell. We could also talk about chemical properties. Okay, so the chemical properties of tellurium must be more similar to selenium, sulfur, and oxygen. And iodine's chemical properties, you would suggest, would be more similar to bromine, chlorine, and fluorine. So therefore, I think any one of those three things will get you the mark. Let's go back and smash that in. So the justifications are tellurium has one less proton, or what was it? I've already forgotten. 56 protons compared to 57. Or we could say tellurium has similar chemical properties to other group 7 elements. Okay, so or we could just say it has 6 electrons in the outer shell. Iodine has 7. So there's quite a few. I can't fit too many more in there. A sample of tellurium is analyzed in a TOF, time of flight mass spectrometer, using electron impact ionization. Give an equation, including the state symbols for this ionization. Why don't you pause the video, see if you can write this out? Okay, I'm going to go through it. So there's a couple of ways to do this. So we can do TE. Oh, I've gone green. I didn't even know that had happened. Right, we can go TE. Now it's going to be in the gaseous state. So everything's going to be gaseous here. And TE starts off like that. It gets smashed by an electron. And what we can show is it becomes TE gaseous. So this is like ionization energy, basically. So I wonder if that will be acceptable. Here, some people like to do this and they're like, yeah, look, Bob, you haven't shown it getting hit by an electron. So they're like, we'd like you to show that. So if you want to show it getting smashed by an electron, because in electron impact, and this says impact, where did it say impact? You are smacked by a beam of electrons from an electron gun. So this electron would smash into tellurium's outer shell and remove one of the valence electrons. So they would both end up bouncing off. And so what you end up with is tellurium positive charge. Oh, I forgot the positive charge there. Look, wash. But here, if you do this version, you have to show that it's knocked an electron off and the electron that impacted also came off. So it's kind of like this situation. Here's tellurium. Here's the electrons. The electron smashes in and then knocks an electron off of the shell, but it also knocks itself off. So you get two coming off. The electron hits and then they both come off. So you can show it like that or like that. Make sure they're in the gaseous state. Make sure TE is plus, and there we go. Bosh. Let's move on, eh? I'm sensing a TOF calculation. Oh my God. Yep, we can see it right there. So 1.4, in the time of flight mass spectrometer, an ion of an isotope of tellurium with a mass number Y travels along a 1.25-meter flight tube with a kinetic energy of 1.88 times 10 to the minus 12 joules. The ion takes 3 times 10 to the minus 7 seconds to reach the detector. Kinetic energy is equal to half mass velocity squared. This is where the kinetic energy is measured in joules, the mass is measured in kilograms. Velocity is measured in meters per second, and calculate the mass in grams. So we need to calculate the mass in grams of 1 mole of these tellurium ions. That's the first step. Use your answer to suggest the mass number Y of the tellurium isotope. So we're looking not at the mass number, the relative atomic mass, but the mass number of an isotope. And so that will catch a few people out. The Avogadro's constant L is equal to 6.022 times 10 to the 23. We can just call it L, and this is worth 5 marks. Why don't you grab your calculator, grab a pen, grab some paper, have a go at this one, and then I'll go through the explanation for you. Okay, so first of all, in these time of flight ones, you're going to need to, well, the best thing to do in an exam is go through and highlight all your stuff. So you're like, right, I've got the distance. Again, let's do this properly. So I've got distance, I've got D, I've got seconds, which is T. So I can do speed or velocity equals distance divided by time. So we can actually work out V. So that would be the first step. We've got the length of the tube and the time. So I would do that first and we work out the velocity, and that will get you your first mark on the board. So let's go ahead, smash that in the calculator and work that out. So we want to do 1.25. We want to divide that by 3 times 10 to the minus 7 seconds. Of course, that hasn't taken long at all. And that is 400 and what the hell is that? That's a big fat number. Okay, so what we do when we smash that in, guys, we're going to go, let's put that here, 1.25 meters. Divide that by 3 times 10. Yeah, 3 times 10 to the minus 7. And that is going to get me 4, 1, and 5 sixes. All of my days, 4, 1, 1, 2, 3, 4, 5, dot 667, and that is meters per second. Okay, so yeah, I've put the old slash rather than m to the s minus 1, but who cares, eh? Right, so that's going to get us our first mark on the board, and that is for working out the velocity. Now that I know the velocity, I want to rearrange the KE equation over here to isolate mass, because we need to calculate the mass. So I want to isolate the mass, so let's do that. We can times both sides by 2 to get rid of the half, so that would end up being like this, 2 KE, oh gosh, he's using green, equals mv squared. Then we'd say to ourselves, hold up, folks. I want to divide both sides by velocity squared. So we're going to end up with 2 KE equals divided by velocity squared. And that is going to give me the mass. So let's go ahead and do that right now. So what is the joules? Aha, I didn't identify joules, and joules was over here, 1.88 times 10 to the J. Now that, of course, is the kinetic energy. So we know the kinetic energy. So we're going to smash this in the calculator, and you're going to do 1.88 times 10 to the minus 12. We want to times this all by 2, and we might as well do that first of all, and then we can set out our calculation nicely. So 1.88 times 10 to the minus 12 times 2, and that gives me 3.76 times 10 to the minus 12. So 3.76 times 10 to the minus 12. Now what do I want to do with that number? I want to divide that. So I want to go 3.76 times 10 to the minus 12, and I want to divide that by the velocity squared. So we're going to do our 416. Gosh, that was a lot of sixes, isn't it? Yeah, that's the serious velocity, and we want to square that. So what is that going to give us? Now, if you're pretty crappy with your scientific calculator, you could flop hard on this. So if you're really bad with your scientific calculator, what you would want to do is write this down first. So 4166666.667, and you'd want to square that first, square the velocity first, and you get like you get this situation. So just simplifying it, because some people, like when they put stuff in the calculator, it always goes pear-shaped. So this will give you 1.736. Jeez, how many ones is that? That is 6 ones. 1, 2, 3, 4, 5, 6. So it's always a nightmare when you're having to type all this stuff out. Normally I just round as I go, but if I round as I go, I won't get the mark scheme answer, and then people get really upset on the chat. They're like, no, your answer wasn't exactly correct. And there we go. So we want to work that out. So let's do it. And if we do that, we get 2.1656 times 10 to the minus 25. So we're going to get 2.16576 times 10 to the minus 25. And that, my friends, will be the kilograms. I know that is a tiny amount. That is the kilograms, the mass that one tellurium ion has. So we've worked out the mass of the tellurium ion. What did the question want us to do? By the way, by this point, we would have scored at least 2, possibly 3 marks, but there's still a fair bit to do. So calculate the mass in grams of 1 mole of these tellurium ions. Right, we don't do that, so we haven't even done that yet. So maybe we wouldn't even get this mark yet. We would have 1 and 2. So now what we need to do is convert this into grams. So it asks us for grams, so I need to convert the kilograms to grams. How do you do that? You times by 1,000. And then also it says 1 mole. We've just worked out 1 ion, because if you read the question, it says an ion. The data we've been given is for an ion. So we need to turn it into the data for a mole. So first we times by 1,000. So let's do that right now. 1, 2, 3. And I get 2.16576 times 10 to the minus 22. So let's write that out. That equals 2.16. Oh my days, this is like yeah, you definitely, I am growing a beard while watching this, or you should be growing a beard while watching this, because this is long. So that's how many grams for 1 ion. Okay, that's a really tiny amount, right? 22 zeros in front of 2.16. That's a real small amount of mass. Let's work it out now for a whole mole. So we want to times by L. Now, L, of course, is over here, 6.022. So times that now by 6.022 times 10 to the 23. And what you're going to get is 130.422. So, and that is going to equal, for me, 130.4. Of course, if you round it on the way, I'm getting 220.672. And that is going to be how many grams mole to the -1, whatever. That's grams per mole. Okay, so they asked me to work out how many grams per mole. So, yeah, that's how many grams there are in 1 mole, 130.4. Now, that is going to get me a mark. Now, personally, we should round that. And as the 2 is smaller, I'm going to leave it to 1 dp, and I'm going to leave it as 130.4. Oh, 139. Feeling fine? No, 130 G per mole. Okay, now what I want to do here is go to the next bit, the fifth mark. Use your answer to suggest the mass number of the tellurium isotope. Now, this is where people might make a mistake. If we go over to our periodic table, is that going to screw things up? Possibly. If we go to our periodic table, look at sulfur, 32.1, look at chlorine, 35.5. Say, oh, you can have decimals for these. Yeah, but chlorine 35.5 is made of two isotopes. One is chlorine 35, one's chlorine 37. Isotopes have a whole number, an integer for their mass number. Why? Because you can't have half a proton or half a neutron. Okay, so the reason why we have decimals like argon 39.9 is because this is the mean mass of the different isotopes taking into account their abundance, remember. So actually, it's impossible to have a decimal if you're doing the mass of an isotope. So when it says what is the mass number of the tellurium isotope, it's not saying the tellurium atom, that would be the RAM, it's saying the individual isotope. So we need to round this, and so I'm going to go for 130, as mine is closer to 130 because it's 130.4. So I'm going to say Y equals 130, and that would get me the fifth mark. Now, with your working out and your roundings, if you'd rounded all the way, you might end up with 131. It depends how you round it all the way. But there we go. Don't forget, guys, it's really helpful if you smash the like button. That massively helps the algorithm because these walkthroughs take me absolutely bananas long time to do. And there's more questions. Tellurium has several other isotopes. Two of these isotopes are 126Te and 124Te. A different sample of tellurium is analyzed using a time-of-flight mass spectrometer. Which statement about the kinetic energy is correct? The kinetic energy of 126Te plus is greater than the kinetic energy of 124Te plus. The kinetic energy of 126 plus is the same as the kinetic energy of 124Te plus. The kinetic energy of 126E plus is less than the kinetic energy of 124Te plus. Now, what we do know is that they are accelerated until they all have the same kinetic energy. And that's just one of the facts you have to know about time of flight mass spectrometry. Time of flight mass spectrometry, regardless of the mass. So regardless of their individual masses, like that's 124, that's 126, that's heavier. If you give them both the same kinetic energy, then because this one has lower mass, in order to have the same kinetic energy as this one, let's just write the equation so I can make sense of this for you. Ke is equal to half mv squared. Now, why do we want them to have the same kinetic energy? There's a really important point. We want these two isotopes to arrive at the detector plate at different times. That's very important that they arrive at a different time at the detector plate, which means they must be going at different velocities because they're going to get there. One is traveling faster than the other, and our light one will always be traveling faster. Why is the light one traveling faster? Well, if you have the same kinetic energy, but you have a different mass, if your mass is lower, you must have a bigger velocity in order to have the same kinetic energy. Right, let's get to the marks. This question is on titrations. Why don't you pause the video and have a go at the question, and then I'll go through the walkthrough with each stage. All right, let me go through the stem of the question first. So question 2. This question is about an experiment to determine the solubility of strontium hydroxide in water at 20 degrees. Strontium hydroxide is slightly soluble in water. Strontium hydroxide solution reacts in a similar way to calcium hydroxide solution. Some solid strontium hydroxide is added to approximately 1 decimeter of distilled water in a stoppered flask. The mixture is kept at 20 degrees. Every day the mixture is checked. If no solid is present in the flask, more solid strontium hydroxide is added. On the day when no more solid needs to be added, the flask is opened and the mixture is filtered into another flask and stoppered. A 25 centimeter cube sample of the filtrate is transferred to a conical flask with a pipette and a few drops of indicator added. This sample is titrated with zero point 0.1 mole per decimeter hydrochloric acid. The titration is repeated several times with further samples of filtrate. The results are shown in Table 1 on page 8. So the results are shown down here. We can see Table 1 is there. Let's go back up. Okay, 2.1. Suggest why the solution is kept until no more solid needs to be added. Okay, 2.2 suggests why it is important to remove the undissolved strontium hydroxide before the titration. And 2.3, after the filtration, the solution is stored in a stoppered flask. Suggest the reason for stoppering the flask. Pause the video, have a go. Okay, I'm going to go through the answers. So, suggest why the solution is kept until no more solid needs to be added. So what they're doing here, they're adding this strontium hydroxide, which is sparingly soluble, and then they're leaving it to ensure that as much strontium hydroxide as possible can dissolve in that set amount of water. And they are trying to make a saturated solution. So to make a saturated solution, or you could say, if you prefer this wording, to ensure, yeah, let's just stick with a saturated solution. I was going to say to ensure the maximum amount of strontium hydroxide that's possible dissolves in the water. So there we go. That's going to get us a mark. Suggest why it's important to remove the undissolved strontium hydroxide before the titration. So in the conical flask or in their beaker, they've got this strontium hydroxide. They've got excess solid strontium hydroxide floating inside there. We need to filter that off, because when we start adding the acid, when we're doing the titration, and remember we're titrating it with hydrochloric acid, we're going to use the molar amounts to calculate the concentration of the strontium hydroxide, because we don't know the concentration of that solution. And so if there is any strontium hydroxide left just floating, that's going to react with some of the acid, and we are going to get a larger result. We're going to think that more acid was needed to react with the solution, when really it's not reacting with the solution, it's reacting with the unreacted floating strontium hydroxide. So what we want to say here, because the excess strontium hydroxide, I say excess, the undissolved strontium hydroxide is what I mean, will react with the HCl. What is HCl? It is acid. So HCOAQ is acid, and this will result in a larger titra. This will result in a larger titra. And also that, what is the result of that if you have a larger titra? It means if we're trying to calculate what the real concentration of the strontium hydroxide is, we're going to get, our concentration is going to end up being too high. We're going to think it's stronger than it really is, because the acid has been getting neutralized by some of the undissolved strontium hydroxide. Anywho, let's move on before I waffle and you grow a big fat beard. 2.3. After the filtration, the solution is stored in a stoppered flask. So just a reason for stoppering the flask. So there's a couple of reasons why you stopper the flask. The main one for me is that you want to put a bung in the top of the volumetric flask after the filtration or whatever, because you don't want any of the water to evaporate. What would happen if water evaporated from the flask? Well, it would change the concentration. The volume would change. So we want to prevent evaporation of water. So we want to prevent the evaporation of water. And I've just noticed that I have spelt saturated way wrong over here. So it should be like that, saturated. Coolio. All right, let's move on, because I am taking ages on this paper. I don't know why, but I'm in a waffling mood today. 2.4, the diagrams in figure 2 show the part of the pipette with the graduation line. Which diagram identifies the pipette that is correctly filled? So a pipette is an instrument called a volumetric pipette, and we use that pipette to transfer accurate volumes or precise volumes of liquid from one place to another. Now, which of these, this is the graduation line, which of these have we correctly filled the pipette? And you should know. Why don't you have a go? And the answer, the correct answer I'm going to explain here, is C. And the idea is that when you have a liquid, you're going to get this thing called the meniscus. The meniscus is this bend. You need to make sure that the bottom of the meniscus, the bottom of the bend, rests on the graduation line. And so it always has to be like that, okay? That would be saying the top of the meniscus, the top of the curve, rests on the graduation line. It's the bottom of the meniscus that must rest on the graduation line. Okay, let's move on. Don't know why it's coming out in purple, but there we go. Okay, here we go. 2.5. Solubility can be quoted as G of solute per 100 centimeter cubed of solution. That's grams of solute per 100 centimeter cubed of solution. Table 1 shows the results of the titrations between strontium hydroxide and hydrochloric acid. These can be used to determine the solubility of strontium hydroxide. So we want to find out how soluble strontium hydroxide is. Okay, we've got the final burette reading and we've got the initial, so we can work out the titra. You work out the titra by doing final minus the initial, and they've done a rough titration. Now, you never have to pay attention to the rough titration. That is purely, yeah, you don't need to pay attention to that, guys. Right, give the equation for the reaction between strontium hydroxide and hydrochloric acid. Use the results table. Use the results in table 1 to calculate the mean titra. Use the mean titra to calculate the solubility of strontium hydroxide in grams per 100 centimeter cubed of solution at 20 degrees. So I'm kind of looking like you're going to get a mark for that for giving the equation. You're going to get a mark for calculating the mean titra, and then 4 marks for this calculation, which will enable you to work out the solubility of strontium hydroxide in grams per 100 centimeter cubed. Why don't you press pause on the video? Have a go at this one with your calculator, your pen and your paper. All right, I'm going to go through the answers. So let's go. First things first, we need to write a reaction between strontium hydroxide and hydrochloric acid. Now, they told us somewhere in the stem, far up there, they told us that it reacts in a similar fashion to, oh my gosh, I can't speak, to calcium, didn't they? So I'm going to write it here. So what was it? Strontium. What is the symbol for strontium? I think it's Sr. So it's going to be strontium hydroxide. Now, strontium hydroxide is in group 2. Well, strontium's in group 2, and hydroxide ions have a charge of -1. So with that in mind, we should be able to formulate an equation. Strontium hydroxide must have the formula Sr bracket OH with a little baby 2 afterwards. Now, what else do we need to know? It's reacting with hydrochloric acid. And do we need to put state symbols for this? Maybe, maybe not. And hydrochloric acid will be AQ, and so will the strontium hydroxide is going to be solid. No, it's not. It's going to be AQ because we made a solution. I'm talking at my bum. Why wouldn't it be solid? Well, they filtered off the excess solid, the undissolved strontium hydroxide. So we're left with the solution, and that's what we're going to want to find the solubility out. Right, so we're going to react this hydrochloric acid with that, and what are we going to make? We're going to make strontium chloride. Now, chloride ions are -1, so we're going to get the similar situation. It's going to be SrL2, and we are going to get H2O because you're going to make acid and base, acid and alkali. You're going to make salt and water. So my salt is going to be aqueous, and my water is liquid, I believe. There we go. Right. Okay, is it balanced? One SR. I've got 2 H's there, 2 O's. I've got 1 H there. That's 5 H's altogether. If I come over here, no, it's not balanced, is it? I need another Cl, so that's going to take care of that and make it 6 H's. No, 1, 2, 3, 4 H's. Sorry. Oh my God, I can't add up. So there were 2 H's there, 2 there. That's for 2 O's and 2 O's. Yeah, we're balanced now, guys. We're balanced now. Oh my gosh, that was difficult. Sorry, I couldn't fit it in. No, did he? Right, let's move on. Okay. So what we got going on? We have we got the equation. So that's going to give us a mark, isn't it, for that lovely equation over here on the right-hand side. We're now going to use that. We're now going to calculate the mean titra. Let's do that bit next. Okay, so for the mean titri, what I'm going to look at, we want to get rid of the rough. You never use that. We want to find concordant results. So let's look at the titra. 32.45, 33, and 32.4. Right, we can get rid of that. Why? It's not within 1 decimal place. These guys are within 0.1 of each other. And so we're going to add these 2 bad boys together. We're going to divide by 2. So the mean titra is going to be 32. Oh my days. I'm writing in white on a white page. That is just dumb. 32.40 plus 32.45 and then divide by 2. So what does that give us? 32.40 plus 32.45 divided by 2. That gives us 48 point, what the hell? I think I've gone a bit bonkers, folks. Yeah, I've gone bonkers. 32.425. How did I not know that, eh? Well, gone a bit bonkers. And that's centimeter cubed. Right, we've got the mean titra. So that's how much hydrochloric acid it took to neutralize the strontium hydroxide. That is going to get us another mark there. Now, you could round that to 42.3, and on the mark scheme, they might tell you, sorry, I can't even speak today. You could round that to 32.4 32.43. And some people on mark schemes will do that, but you could equally keep it as 32.425. But if you want to go to 2DP, 32.43. Okay, let's zing on because we've got another 4 fat marks to get here. Use the mean titer to calculate the solubility of strontium hydroxide. So what I want to do here is calculate the moles. With titrations, you're always going to need moles. We love some moles. So N over C times V. And I'm going to be able to calculate the moles of acid. Why? Well, I know that this is how much hydrochloric acid was used. And when we told the concentration of the hydrochloric acid solution, I believe we were, and I'm going to scroll up for 2 seconds just to check. I believe we were told it was 0.1. Got to go all the way up here. Check that out there, guys. 0.1 mole per decimeter of hydrochloric acid. And we're doing that against 25 centimeters of strontium hydroxide solution. So let's scroll back down. I didn't want to delete all my bits. So we've got 0.1. So conc equals 0.1, and that's going to be mole dm minus 3. And our volume is obviously 32.425. Now that's centimeter cubed. Notice there's a clash. I need to turn the volume into mole. I need to turn it into decimeter, sorry. So I need to divide by 1,000, so to speak. And that is going to give me 0.032 425. There we go. Oh my gosh, 32. Something wrong with my button. 425. And that is dm minus 3. Oh, dm. Gosh, I'm going crazy. So there we've got the volume. There we've got the conc. I want to multiply C times V. So, and that is going to give me moles of hydrochloric acid that were used. And that is going to enable me to know how many moles were in the 25 centimeters. So let's do that. So let's work out how many moles of HCl there were. So I'm going to go 0.1. I'm going to multiply that by 0.032425. Sounds like a telephone number. And that is going to give me 0.032425. So 0.00, sorry, 32425. So we've got an extra zero, of course, because we times by 0.1. So that is moles. And you might be thinking, with titrations, it's always good to make a note of what you just calculated. So that's moles of acid. Now I know the moles of acid, that we got rid of the undissolved. So that is telling me how many moles of strontium hydroxide were in the 25 centimeters. How do I know that? Well, let's check the ratio. It's 1 to 2. So we have a ratio of 1 to 2. So I'm going to have half as much strontium hydroxide neutralized this here. So I need to do my next calculation. The ratio is 1 to 2. So we have half as much SrOH2. So we have half as much. So I'm going to need to do 0.0032425 divided by 2. And that is going to get me 0.0016225. So that gives me 0.00162 125, and that is moles of not but moles of strontium hydroxide solution. Right, we've now worked out the moles. Now you might think, what normally in titrations your next step is to go ahead and work out the concentration. We're not really bothered about the concentration here because we're going to turn this into grams because they want to know how many G's in 100 centimeters. Well, that's how many moles are in 25 centimeter cubed. Remember, this was in the stem right at the top of the question. This was a 25 centimeter cubed sample. So we want to find out, okay, how much is in 100? So we're going to get a mark for working out the moles of the hydrochloric acid, and we should really get a mark for working out the moles of the strontium hydroxide. And now what we need to do is times this by 4. So times 4 times our moles by 4. You could turn it to mass and times that by 4. I'm timesing it at the mole stage. It doesn't really matter which stage you times it by 4, but there needs to be a times by 4 in there. I now know that I've got 0.006485 moles in 100 centimeter cubed, and all we've got to do to find out the solubility is find out how much that is in grams. So what we're going to do now is work that out in grams. I know I've got that many moles, so I'm going to need to bust out the equation. You know the coup. It is mass over mr times moles. So mass equals Mr. Moles. And of course, mass is in G, and that is what we were after. As it said here, calculate G per 100. So we now know moles. So we're going to do 0.00648 and we're gonna times that by mR of strontium hydroxide. What the hell is strontium hydroxide? I can tell you that 17 times 2 is 34 for the two hydroxides, but what is the strontium ion? Is it 86? Let's check it out. I've got the periodic table somewhere up here. Bosh, where are you, strontium? 87.6. I knew it was a roundy, something like that. Okay, so we're looking at 87. Whoa, 87.6. Okay, so we're going to times this by bracket 87.6 plus 17 whoops times 2. So yes, how am I going to work that out? Let's do that. Okay, times 87.6 plus 34, close bracket, and that equals 0.788576. So that equals 0.788576. And why am I typing in black on a black screen? I have no idea. Can I do this in it? Can I change the color of this, please, Bob? Can I change that? Are you going to let me change that? No, you're going to let me change that. I better put that in white here. Okay, guys, because can't really see that on that screen. So that's what we're looking at. That's the MR. Okay, that's the MR of strontium hydroxide. And so what we've just worked out here is we've got 0.788576 G per 100 centimeter cubed. And there's your final marks, final pieces of the puzzle. Now, do I want to am I going to get the mark for that, or do I need to round it? I think we're either going to go to 0.789, three significant figures, or we go to 2 DP, 0.79 grams per 100 centimeter cubed. What do you think? This is where I'll probably flop, but I'm going to go to three significant figures. It's my when in doubt, do three significant figures. And so I'm doing that per 100 centimeter cubed. There we go. And that's my final answer. So that should get us all of the mocks. Boom. Okay, welcome to Let's Get to the Mocks. Going through something on complex ions here, little chemistry A-level questions. So why don't you pause the video at the start of the question and then unpause and watch the explanation. This question's about aqueous ions of the metal ion. When an aqueous FeH2O6 3 plus ion reacts with ethane-dioate ions, an iron 3 complex ion X is formed. Only ligands in X are ethane-dioate ions. Draw the structure of X and include the charge. Right, ethane-dioate ions have the formula C2O42 minus. Kind of look like this, so giving you a little bit of a helping hand here, peeps. Why don't you press pause on the video, have a go at this with a pen and paper, and then unpause and watch the explanation. All right, so we've got our ethane-dioate ions. They want us to include the charge and draw the structure. So we get 1 mark for drawing the structure and 1 mark for including the charge. Okay, so remember this has got a 3 plus charge, this ion, and it's in the middle. And we're going to draw our ligands around them. Now, ethane-dioate is a bidentate ion. Bidentate ligand, sorry. Ligand is the molecule that bonds to the central metal ion. So we're going to have 3 ethane-dioates around here. Each one forms 2 coordinate bonds. A coordinate bond is this solid black line, this covalent bond here. I need to make those they look like forces. Those first 2 I've done with a dash line. I need to make them solid. So these should all be solid, and you've got 3 ligands around here. Each ligand is an ethane-dioate molecule, and of course 6 covalent or coordinate bonds around the ion. Now, how are they able to do that? Well, they had a minus charge and the ion had a 3 plus charge, but overall there are still 3 minuses spare because obviously it's 3 plus, but there is 6 minus from each one of those 6 oxygens. So if you take 6 minus and 3 plus, you're going to get an overall 3 plus outside the minus 3 outside the bracket. Sorry, minus 6 plus 3 is minus 3. There we go. We can get rid of the charge on the ion, and that is going to get you 2 marks. You should do solid black lines for those coordinate bonds. And there we go. Yeah, ethane-dioate is an example of a bidentate ligand. Right, the formation of X is an example of the chelate effect. Explain the meaning of the chelate effect. Okay, so the chelate effect is when our multidentate ligands, like ethane that we just saw, which is a bidentate ligand, dentate means teeth, so it has like more than one set of teeth, replaces a monodentate ligand, something like water, which only can form one coordinate bond for each of the ligands. Each water molecule can only form one coordinate bond with the central metal ion. So when a multidentate ligand replaces a monodentate ligand like water, what happens is it reduces the number of overall particles in the solution. And sorry, it increases the number of overall particles in the solution. Get myself all in a mix. And therefore, it increases disorder and increases entropy. So we can write out the reaction to show this. Okay, I've just had to rewrite my answer because my internet went off and I lost everything for a second there. So that was a pain in the butt. Right, I'm going to write an equation. So once again, this is because multidentate ligand replaces the monodentate ligand, increasing the total number of particles and so forth, increasing the disorder or entropy. So we've got our molecule here. What the hell is this? This is like a hexa aqua, meaning 6 water, um, iron 3 ion ion. Okay, so hexa aqua, iron 3 ion, and that reacts with our 3 ethane ions. So in total there is actually 4 particles here. You've got the hexa aqua yeah, iron 3 ion, and it's reacting with 3 ethane so 4 particles. What have you got afterwards? Well, those 6 water molecules have been pushed out, right? They've been bumped off and displaced. So you've actually got 7 particles on kind of the product side of this reaction on the right hand side. And that means you've increased the total number of particles in the solution, and therefore you've increased entropy and disorder. And it's going to favor shifting to this side of an equilibrium. Okay, cool. Let's move on. 3.3, outline how Fe2 plus ions catalyze the reaction between S2O82 minus ions and I minus ions in aqueous solution. In your answer, you should include a sketch graph to show how the concentration of S2O82 minus ions changes over time. And we need an explanation of how the Fe2 plus ions catalyze the reaction, including equations. And stage 3, we need an overall equation for the reaction. Now, why have I written stage 1, stage 2, stage 3? Because in the mark scheme, they're going to basically award you points, whether you're a 1 to 2 level, 3 to 4, or 5 to 6 marks. And if you want to get 5 to 6 marks, you've got to complete all 3 stages. Basically thoroughly. If you just do stage 1 and 2 thoroughly and half of stage 3, you'll kind of get 5 marks. So if you only do kind of half of each stage, you'll drop. But essentially stage 1 is drawing the sketch, and they want to know how the S2O82 minus, like peroxy disulfate ions, change over time. So we're going to write the concentration of the ion on the left hand side and then time at the bottom. And just like any first or second order reaction, it's going to decrease in reaction rate, basically. The reaction rate is going to go down. Why? We have more particles at the start, so it's going to be steeper decline at the start as you've got the highest rate of reaction, more S2O82 minus ions are being used up, and then over time the rate of reaction decreases, and that will be shown by this slight curve. So one for labeling the axes, one for the curve. Now the second stage, an explanation of how Fe2 plus ions catalyze the reaction. Well, we know that S2O82 minus is negative and I minus iodide ions are negative. So peroxy disulfate are negative and iodide ions are negative as well. This means there's a repulsive force from the 2 negative ions repelling each other, a repulsive force. Now that needs to be overcome if you're to force them to react, and that creates a very high activation energy to overcome that and push those together, and so the reaction is slow. Now what the Fe2 plus ion can do, it can attract, because it's positive and S2O82 minus is negative, it can attract to the S2O82 minus, and it what attracts to it and so lowers the activation energy. It doesn't have to overcome that repulsion. So there's a lower activation energy between Fe2 plus and S2O82 minus than there is between S2O82 minus and I minus. Now, because iron, Fe, has variable oxidation states, it can be 2 plus or it can get oxidized by losing an electron to 3 plus. This enables the Fe2 plus to give an electron to S2O82 minus. Now, why would it want to do that? Why would it want to give up an electron? Well, the sulfur can go from a +7 charge to a +6 charge and form a sulfate ion. So that's what happens here. The sulfur gets reduced in the S2082 minus. Now, you might say to yourself, but how do I know that the Fe2 plus ion reacts with S2082 minus? Well, it can't react with I minus, right? It can't give an electron to I minus. I minus cannot take any more electrons. Remember, it's got a full outer shell. It can't receive any more electrons. So what we get going on here, so that should clear up which species the Fe2 plus catalyzes. It has to catalyze S2082 minus because it cannot give an electron up to I minus because I minus has no room for taking that electron. So what happens here, I'm showing you, this is the equation to show how the Fe2 plus forms Fe3 plus by giving an electron to the sulfur atoms in the S2082 minus. You can see that there, the oxidation states +7 goes to +6. You don't need to show the oxidation states, but that's just for your explanation, peeps. Now, the next step of this, we're going to have to reform the catalyst. Otherwise, Fe2 plus is not a catalyst, right? So it's got to go back to being Fe2 plus from Fe3 plus. Otherwise, it's not a catalyst. It gets used up in the reaction. So the Fe3 plus now, because very positive, can approach the I minus, and it can now remove that electron from the I minus and be reduced itself and oxidize I minus. It can oxidize the iodide ions back to iodine. And notice that the catalyst is reformed. So we've gone from Fe3 plus to Fe2 plus. It stole that electron off of iodide and turned iodide into iodine. Okay, now not C. Oh my gosh, I can't spell notice. Not C. I mean notice. Catalyst is reformed. Okay, you won't get marks for writing that. That's just me trying to show you what's going on here. Now, in order for us to get all of stage 3, we kind of, these two parts are really part of stage 3. They're the build up to the overall equation, and we're going to write the overall equation. Now, notice that Fe2 plus appears on both sides of the equation. If you combine these two half equations to make the overall equation, Fe2 plus is going to cancel out because you're going to have two Fe2 plus on either side. You're going to have two Fe3 plus on either side. So I could write it out with the Fe2 plus and Fe3 plus on both sides and then cancel, but I've kind of run out of room for doing that. I would ideally like to do that, but so we're just going to cancel out the Fe2s and the Fe3s because they appear on both sides, and then we're going to be left with S2082 minus plus I minus goes to SO42 minus plus I2, and that is the overall equation, and that is going to get you all of the 6 marks. Okay, so there we go. This one I would get on the back of a revision card as well, because this is quite common, this reaction, the S2082 minus ions and I minus ions and reactions like this. Very, very similar questions come up. Okay, 3.4. A student adds dilute ammonia solution, so that's NH3AQ, to a solution containing FeH2O6 2 plus ions. So what have we got there? Hexa aqua ion 2 ions. Yeah, give the formula of the precipitate that forms. So you have to know these off by heart. You'll find in your CGP or various other excellent revision guides and books all the formulas of your complex ions and how they react, and you just got to learn those off by heart. So you're going to get FeH2O4 OH2, and there's going to be no charge outside the brackets because a 2 plus ion and 2 hydroxides, the 2 minuses cancel out the 2 plus on the ion at the center. Okay, so there we go. The student then adds sodium carbonate solution to a solution containing FeH2O6 2 plus ion. State one observation the student would make. Give an equation for the reaction. Let's write out the reaction first of all, and then we probably can spot the observation from that equation. Okay, so our sodium carbonate is being added to our, I hate saying this word, but our iron hexa 2 ions, right? 2 plus ions. And we're going to get, we don't get any fizzing here. We don't get carbon dioxide released. We're going to get FeCO3, so iron carbonate, and we're going to get 6 water molecules released. So there's no fizzing, no effervescence. We get some sodium ions as well. And the observation, well, we're going to get a precipitate, a pale green precipitate. So we're going to see a pale green precipitate. And of course, something happens to this. If you leave this green precipitate standing long enough, it changes color. And we'll come on to that in the next question. So the observation is a green precipitate. So you see a green solid form. And you're going to pick up your marks for your equation as well. And we're now going to go on to 3.6. A solution containing FeH2O 6 2 plus ions. So again, changes to a yellow-brown color after several hours in contact with air. So that's what happens. The Jeez Louise. Hexa aqua iron 2 plus ions actually change to hexa aqua iron 3 plus ions. So that means that the iron gets oxidized and goes brown. It goes the color of rust. You think when Fe3 plus, Fe2O3, like iron oxide, rust is a reddy brown color. This goes yellowy brown. So again, it's in the Fe3 plus state. It gets oxidized basically. So the sodium adds the student then adds sodium carbonate to this FeH2O6 3 plus. Okay, so the hexa aqua iron 3 plus ions are added to carbonate ions, and what we get formed is over here on the right hand side of the equation. And of course, that has a brown oh jeez Louise, look, I forgot in my equation to put 3 plus, I put 2 plus. What an idiot. Right, so you can see this is oxidized first of all upon standing, so it goes from a green precipitate to a yellow brown precipitate. It loses an electron and it becomes Fe3 plus. That's why Fe2 plus has that green color. Fe3 plus, generally you get these yellow and brown colors with Fe3 plus. And there we go. That's the equation that you need to know. And this one does effervesce. So this one does fizz. So that's the difference when you react Fe2 plus or hexa aqua iron 2 plus ions with carbonate. You don't get fizzing, but you do get the fizzing when you react, oh my gosh, hexa aqua iron 3 plus ions with carbonates. Whoo! Welcome to Let's Get to the Marks. Going through question 4 of the 2024 A-Level Chemistry Paper 1 for AQA. This one's on KP and it's got a little bit on the units and stuff like that. Let's get straight into it. Let's go. This question is about gas mixtures at equilibrium. The reaction can be used to make hydrogen. We got water gaseous plus carbon monoxide gaseous, reversible symbol, hydrogen gaseous plus carbon dioxide gaseous as the products. We've got an enthalpy for the reaction, an enthalpy change, which is minus 41 kilojoule per mole. Hopefully you know what the minus means. A mixture of 2 moles of water gaseous and 2 moles of carbon monoxide gaseous is allowed to reach equilibrium at a constant temperature in a 20 decimeter container. At equilibrium, there are 0.92 moles of hydrogen gas. Calculate the mole fraction of hydrogen in the equilibrium mixture. We need it with 2 marks, peeps. And yeah, let's calculate the mole fraction of hydrogen for 2 marks. Why don't you press pause on the video, grab your pen, grab your paper. You might need a calculator for this. You shouldn't do. You can do all these in your head, but have a go. All right, I'm going to go through the way that I do it. It's not always the best way, but it's the way that I do it, and hopefully some of you will find it helpful. So I need to calculate the fraction of hydrogen in the equilibrium mixture. Guess what? It's equilibrium. We've been given the kind of initial moles of the reactants. So what we're going to need to do is the old ICE, bit topical at the moment, ICE, but yeah, we got to do a little bit of this. So a little bit of that, a little bit of this. So here's ICE, ICE. What does it stand for? Initial, change, equilibrium. So this is my H2O. I'd write that there, carbon monoxide there, hydrogen there, and carbon dioxide there, but you get the coup. There's nothing really needed over here. So what we're going to do, a mixture of 2 moles of water. So I know I've got 2 moles of water. Oh, and 2 moles of carbon monoxide. So I know I've got 2 moles initially of carbon monoxide. Now, initially, you can't have any product. Okay, so these will always be 0 on the product side. And then it's going to give us, it has to give us something that's changed for us to work out the equilibrium. We only need one thing, so let's check it out. At equilibrium, there are 0.92 moles of hydrogen. So we know that at equilibrium, there are 0.92 moles of hydrogen. That don't look like a 9. Maybe it does now. 0.92 moles of hydrogen at equilibrium. Let's make that dot a little bit bigger. And so what we're going to do is we're going to say, well, how much did it change by? Well, if it went from 0 to 0.92, it changed by 0.92. 0.92. Pretty obvious, right? Now, all we're going to do is look for coefficients. Oh my gosh, this one's nice and easy. Look, they're all one-to-one reactions. So what that means is if this changed by 0.92, then the one next to it changed by 0.92. And that means that also had 0.92 at equilibrium, the carbon monoxide. But what about these guys? Well, they changed by 0.92 as well because it was one to one. So everything changed by 0.92. So they made this one kind of nice and easy for us. But how much was left after they changed by 0.92? Well, they went down, obviously. So we had 108 left and we had 108 left. So we need to work out the mole fraction, and it is of hydrogen, and it is what it is. How much of the total at equilibrium is the hydrogen? Well, I need to do 0.92 because that's how many moles of hydrogen we have at equilibrium over the total moles. And if I go 0.92 plus 0.92, 1.08, 1.08, I believe if you take those two little 0.8s and add them there, we're going to get 1, 2, 3, 4 moles. So 0.92 over 4. Where's my calculator? Because I ain't smart enough to do that. 4 point something, who knows? 0.92 divided by 4. Oh, shows you I'm talking out my backside. It's 0.23. Okay, I think I was doing it the other way around. 0.23 is the mole fraction for hydrogen. Let's just double check that because my maths can be shockingly bad. And that will get you 2 marks. Now, if that's helped you, make sure you hit the like because that's really useful to me. Aha. 4.2, state why the equilibrium constant Kp for this reaction has no units. So we're going to write out the Kp for this reaction. And hopefully you know Kp, same as Kc, guys. So we're just doing reactants, products over reactants, P over reactants. The only difference here is these bad boys are in curvy brackets because it's kPa, it's pressure, and we put the coefficients outside, but because they're all 1 to 1 to 1 to 1, there's no coefficients. So essentially it's like, yeah, you get the idea. Anywho, what I want to show is that we would have hydrogen times carbon dioxide over the Kp of H2O times carbon monoxide. So we'd essentially end up with this kPa times kPa, like that. So, and then we would have, these are the units. And at the bottom for the reactants, we'd have kPa for the water and kPa for the carbon monoxide, and they wouldn't be squared or anything like that. So it's just a straight thing of there's no units because the kPa cancels for the reactants and products. So we want to say kPa of the reactants and products are in equal kind of ratio, so cancel. Yeah, so they're going to cancel out. So that is really what we want to get down. Okay, let's move on. Keep moving on, keep moving on. Right, 4.3, the temperature of the equilibrium mixture formed in question 4.1 is increased. How does the amount of hydrogen change when the new position of equilibrium is reached? So basically, they're asking us about the yield of hydrogen gas. The yield is always on the right-hand side in these things because that's what we want to make. We want to make the hydrogen, and they've increased the temperature. Now, check it out. What does that mean? That means it's exothermic, this reaction. What does Le Chatelier say? Le Chatelier, and I always think of in my head, exothermic reactions are hot, and that means that this side of the reaction's hot. This side over here, the left-hand side or the backward side is endothermic, and to me, that's cold. I know it doesn't, it isn't in reality, but we're just saying that's the cold side, that's the hot side. If you increase the temperature, Le Chatelier says it's going to do the opposite, right? So he's going to move backwards and you're going to get a smaller yield of hydrogen. The yield of hydrogen is going to decrease for those reasons, because if you increase the temperature, the reaction goes, no, I'm not having it, bruv, I'm not having it. And it shifts the other way to make it cooler again. And so you get a lower yield. So for this particular reaction, to increase the yield, you wouldn't want to use a high temperature. So let's go over there and say the amount decreases, and that will get us a mark. Okay, what have we got here? Ethanol can be made from ethene and steam. We've got ethene plus steam, because it's water with a G. Reversible goes to ethanol. And the enthalpy change is minus 45 kilojoule per mole. Table 2 shows the mole fractions of each of the gases in the equilibrium mixture at 6,000 kPa. I'm going to have to scroll down, folks. We don't get a mark for that. That was a random tick. Okay. Oh my gosh, I hate this when they split it like this when you're doing a video and they split that. Okay. Give an expression for KP for this reaction. Calculate the value of KP at 6,000 kPa and state the units. It's worth 4 marks. Let's smash through it. All right, I'm going to go up here to do it so I have all the bits around for it. So what was the first thing? Give an expression for KP for this reaction. So why don't you pause the video, have a go all three of these parts for 4 marks, and then unpause and I'll go through the explanation. All right, let's go, let's go, let's go, let's go. Boom, boom, boom. Right, what we want to do is go, so KP, as I said before, is products over reactants. So I'm just going with CH3, CH2. It's painful watching me do this. So we're going to go like that. It's really that's the kPa rather than concentration. If it was square brackets, it'd be concentration. When it is curved brackets like that, it's the kPa. And then underneath, I want to do C2H4. And look, there's no coefficients. Very unusual. Both the questions here had no coefficients, so like didn't have a two there. There was a big fat two there. I'd have to put a two there, so just remind yourself of that. But we don't have to at this point. And then we're going to multiply that underneath by the other product, which is H2O or the kPa of H2O. And this is not concentration, it's kPa. So there we go. That is going to get us the first lovely mark. So let's give ourselves a tick and we're all in, got one in the bag. Right. Now what we need to do is calculate the value of KP at 6,000. This means I need to work out the KPs of all these individual ones, and that should be pretty easy. They're giving us the mole fractions. So the mole fraction, to find the KP for an individual reactant or product molecule, you just times the mole fraction by the total kPa, and the total pressure is 6,000. So I need to do that, all of these times 6,000 individually, and then set it all out again. So let's try that, eh? And this is, I'll show you where I always make a mistake. If you're not a natural mathematician, there are some points that you will make mistakes. And I would say that I'm quite good at mental maths, but I'm not necessarily a natural mathematician. So what we've done, ethene here, I've done that times that, and I've got 3870. So that's going underneath over here, 3870. That's the kPa for ethene. And then I'm going to do the steam. What's that? 0.323. 0.323 times 6,000. And that equals 1938. So that's my water. 1938. These are my reactants. And then you always just want to double check. It's easy to mash this up. And then 0.0321. So let's do that. 0.0321. We're going to times that by 6,000. And that is going to give me 192.6. And oh my gosh, it looks like 1,000. So that's 192.6. And that is going on the top. And that is our KP. And all I want to do here, guys, is rub this bad boy out and then let's smash these in the calculator and see what we get. Where is my calc? There it is. Okay, so mm, mm, mm. Uh, oh gosh. Now, what I would say is for some people, they prefer to multiply these at the bottom first. So if you do this and you do it all correctly in your calculator, I'll just show you what you get. You're going to get a really disgusting number. So it's like 0.00002567979. But look, so you can play around with that. If you don't get the correct answer and you keep getting like, oh man, when I put it in my calculator, I don't get the right answer. What I suggest you do, and it's long, but if it comes to a last resort, is you times these two first, and then you write the number out again and do 192.6 divided by the sum of this calculation at the bottom. Because sometimes when people put brackets in and smash things in their calculator, they just have a habit of coming up with the wrong answer. But so we have the kPa. Now we need to work out the units. So, I mean, you might want to put that in standard form. What's that? 2.6. Maybe they'll allow it if we go 2.6 times 10 what is that? To the one, two, three, four, five, to the minus five. And then what would our units be? So let's state the units. And so we have to look what we had here. And this is important. So I'm doing this down here for the units bit. Um, now, if you've got to work the units out for this, well, this means you're left with the same base units. You've got KPA, KPA, and KPA. So what do we do? You write the units out for each of them. And then to work the units out, you say, well, what I'm going to do is I'm going to add these together. So I'm going to go, right, I've got on top, I have KPA 1. And underneath, I have KPA 2. And then all you're going to do is go one lot of KPA minus, so KPA to the 1 minus KPA 2. And that is going to equal KPA minus 1. So you just take from the top, you just take whatever's at the bottom, and then that will tell you whether you're on a minus. So let's imagine we're in a nut. So the answer here is KPA to the minus 1. Now, I think my symbols are a little bit put there, but let me give you some other examples. Okay, just very, very quickly. Let's imagine you had the situation where you had like KPA, KPA at the top and just one KPA at the bottom. Well, we would basically have KPA 2 minus KPA 1, and that's going to equal KPA to the 1, which we just write as KPA. We don't actually bother. The P, by the way, I'd probably lose the marks here because I'm not using a capital P. So that would be a real capital P for plum would be what I would get there. Right. So that would be KPA. We wouldn't bother writing the 1, just like when you're doing coefficients, you don't bother with that. So that's just giving you an idea of how to do it. State the effect, if any, of an increase in the volume of the container on the value of Kp for the reaction at constant temperature. Okay, when you change volume, what happens? So basically, you don't need to write all this, but I'm just going to put it so you can see it's an explanation. So change. Oh, that's disgusting, isn't it? Let's just do it properly. Changing volume changes pressure. However, pressure has no effect on Kp. Just the same way, oh my gosh, as concentration has no effect on Kc. So remember, it's temperature that is going to change the Kp or change the Kc. It is not pressure or concentration. Okay. So basically, we didn't need to say any of that. We just had to say no effect. We just had to state it, no effect, whoops, on Kp. So that's the bit that I needed to say. All the rest of it is waffle. I didn't need any of that, just no effect on Kp. Okay. And the reason why is everything stays in the same ratio above and below the line. So Kp will be the same regardless of what you do to the volume. The pressures will change by the same amount on either side. Okay, right. That's the end of the question. Okay, welcome to Let's Get to the Marks, going through a walkthrough question on chlorine. So, you know the coup, press pause at the start of the video, pen and paper, have a go at the question, and then unpause and watch the explanation. All right, let's go. Pause the video, guys. Right, question 5. This question is about chlorine. Give an equation to show how chlorine forms an acidic solution in water. So they're giving you some clues to start this off. We know that they're talking about chlorine and it's in water, and they've mentioned that it forms an acid. So that's kind of nice for us because we know that we have chlorine, we know that we have water, and we know that we're forming an acid. You can kind of guess which acid you're going to form, right? You've got H and you've got Cl, so you're going for hydrochloric acid, but you're also going to make hydrogen chlorate as well, which is HClO. You can write that if you like. Some people like to write this HOCl like that. Essentially, you have your chlorate ions, your ClO minus and your H plus coming together. Cool, 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 cool. And it's a reversible reaction. I won't bother with state symbols. 5.2, give an equation for the reaction between chlorine and cold dilute aqueous sodium hydroxide. This is just these reactions I recommend putting on a revision card and just learning these off by heart. But here we go. As this is an A2 paper, you might be thinking, oh yeah, they're not going to ask me about chlorine in A level. That's more AS. But you can see right here, this is from the 2024 paper one. A level for AQA. So this comes up in A level too, guys. So make sure you're prepared. Give an equation for the reaction between chlorine and cold dilute aqueous sodium hydroxide. Pause the video. Have a go. All right, I'm going to go through and show you the answer that I would give. So this is what I would do. Chlorine. And again, they're giving us some clues between chlorine and dilute aqueous sodium hydroxide. So we know it's going to be aqueous, but I'm not putting state symbols in as it didn't ask me. So going to be lazy. And what are we going to make this time? We're going to make sodium chlorate like that. So the only difference here between reacting with water, have a look, and reacting with sodium is that instead of an H going on, we've got an Na going on to NaClO. And so you would expect, well, we made HCl, so we're going to make NaCl as well. So it's almost an identical reaction. You're just swapping wherever you had a hydrogen there being added on, we're adding a sodium on there. So instead of hydrogen chloride, we make sodium chlorate. Instead of hydrogen chloride, we make sodium chloride. And of course, what happens is we also get some water being produced. And what I want to do, that one up there looks a bit dodgy because I left this stuff here. Okay. So, and now I just need to balance it up. So I've got two chlorines there. I'm going to need to oh, I've got two chlorines here and two sodiums. So what am I in trouble with? Oh, I've got two oxygens and I've only got one oxygen over here. So I'm going to need a two in front of sodium hydroxide. That gives me the two oxygens. Anything else? Anything else? No, I think that's all balanced, isn't it? Look, I've got two sodium, two sodium. I've got two chlorine, one chlorine there, one chlorine there. I've got two oxygens, one oxygen there, one oxygen there, and two hydrogens, and I've got two times hydrogen. So that is all balanced. Brilliant. Really longing out the video today, but there we go. I've had a habit of doing that lately. I've got to get back to being a little bit more quick with it. In acidic conditions, chlorate ions oxidize chloride ions to form chlorine gas. Deduce the half equation for the oxidation of chloride ions to chlorine. It's not necessarily in gaseous form, but deduce a half equation for the reduction of chlorate to chlorine. Deduce the overall equation for the reaction, and this is worth a fat 3 marks. So why don't you have a go at doing these two half equations and then combining them to make the overall equation? Pause the video, have a go. All right, I'm going to go through the answers. So first off, we've got a nice easy one. It's telling us it's oxidation. Don't forget oil rig. Oxidation is loss of electrons. So we're going to lose electrons here. That means they're going to be on the right-hand side rather than the left-hand side. And it's telling us we're starting with chloride ions. So we're literally going Cl minus, and we're going to chlorine. And of course, in order to do that, it's going to be oxidized. It's going to lose this minus. So we're going to put the electron over here. Now we need to balance it up. There's two chlorine atoms in that diatomic molecule. So I need two chloride ions. And that means it's lost two electrons. And that is going to get us one of those three lovely marks. Right, let's look at the second equation. So some people find these ones a little bit harder. Deduce a half equation for the reduction. So reduction is gain, oil rig, of chlorate ions to chlorine. So we're going to gain electrons here. So I'm going to do, and I'll show you how that all works out. So we're going to go CO, that didn't work out very well there. Right. ClO 3 minus, and we're going to chlorine. Now I need to leave myself a little space either side because I don't know what I want to add in. So we're looking at that and we're going, oh, that's kind of nice, isn't it? But I'm going to need a 2 here straight off the bat because I need to balance that with that. Now, what do I do with all of these blooming oxygens? That means I have 6 oxygens. So what am I going to do with this 2 times 3, 6? Now, why did I have to put a 2 there? Well, because I need 2 chlorines to make chlorine gas. So I had to put a 2 there. And that means I end up with 6 oxygens. Well, when you do this, you're going to write 6H2O. Now, whenever you're doing a half equation and you have oxygen on one side and you need to balance it up, you can add in H2O. And there's always a clue in the stem of the question that you'll need to do that. And notice it says acidic conditions. What does that mean? That means that hydrogen ions are knocking about so that you can make water. So now that we know we've got 6H2 there, that means I need 12 hydrogen ions over here because you'd need 12 hydrogen ions to react with those oxygens to do that. So Wunderbar. We're nearly there, folks. All we got to do is make sure it's electrically balanced. And when I need to do that, I go, well, I got 2 times minus. Okay, so I've got -2, and then I've got 12 plus. That means I'm kind of 10 plus over here. I've got an overall charge of 10 plus, and I've got 0 charge here. So what I need to do is add 10 electrons in here. And remember, we said this is called reduction. Reduction is gain. So obviously, electrons needed to be gained. So we've got 10 electrons joining on here. And that means that with those 10 electrons and the 2 minuses for the 2 chlorate ions, they cancel out the 12 plus there. And you've got the hydrogens and the oxygens to make the water. Boom! We've done the second mark. Okay. Now you've got to do the combining of 2 half equations. And how you combine half equations is you look at the electrons. So there's 2 electrons there and 10 in that half equation. What's the ratio between them? It's 5. I need to balance the electrons so they match. So I'm going to times everything in this half equation by 5. And that means I'll get 10 electrons, 5 chlorines, and 10 chloride ions. And I just need to add all the reactants together and put them down here, and all the products together and put them down here. So let's go ahead and do that and construct our overall equation. So first of all, let's start with 10 chloride ions because we times them by 5. So we've got 10 chloride ions. Then I want to write in my 2 chlorate ions. Then I want to write in my 12 hydrogen ions, and don't forget my 10 electrons. Now, we're going to do a bit of cancelling, so I'm not going to need all of this stuff, but I'm just kind of showing you, all right? So then you'll be able to cancel after. Right, now I need to write in the product. So I've got 5 times Cl2, so that's going to mean I've got 5 Cl2. But oh, hold on a minute. I've also got a Cl2 down here. So let's make that a 6. Handy that 5 and 6 are close. Just whack that in. So now that's taken care of all the chlorines. And then I've got 6H2O. And nice overall equation. But I've got 10 electrons as well. Whoopsie. Now, the 10 electrons I've got on both sides. So I'm going to rub them out. We're going to cancel them out. So you wouldn't actually even bother putting the electrons in. Once you've balanced them there, you know they're going to cancel. So you don't need to put them in. Everything else we need to show because everything else is needed. And then we just check, is it electrically balanced? 2 chlorate ions, 10 chloride ions replace those 10 electrons. 12 plus, yes. Electrically balanced, yes. Electrically balanced. Bish, bash, bosh. Bing. 3 marks. Okay, let's zing down. God, taking a long time over these. Okay, 5.4. Give the equation for the reaction of solid sodium chloride with concentrated sulfuric acid. State the role of the chloride ions in this reaction. Yep, let's do it. Okay, why don't you pause the video, have a go at this 2 marker, unpause, and I'll rinse through the explanation. Okay, here we go. State the, what is it? We're being told that we've got solid sodium chloride. So I'm going to do state symbols here. So I've got sodium chloride solid and concentrated acid, right? Sulfuric acid, H2SO4. That means it's aqueous because it's constant. Well, yeah, because it's an acid. They're always aqueous. I'm not going to have the room because I started that over here. Let me dash this down on the line. 1 second, folks. Hold on while I extend things out. Oh my days. Da, 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 da. Gives me a bit more room to work with, right? Nothing wrong with that. So what's going to happen here? Well, again, put these on revision cards. You need to know them for chlorine, for bromine, and for iodine. They're part of your halide ions reducing ability, and it's part of the topic on Group 7 that you have to know, and of course, it can come up in A level. So what we want to do here, you've got 2 choices. You could do sodium, hydrogen, sulfate. I'll show you the alternative, and that is aqueous. And that is then going to leave us with the sodium has gone there and the hydrogen has substituted there. So you've just sort of swappy around, bit of a swapping situation going on. Now, is this oxidation or reduction? Because it says, what is the role of the chloride ions? So are they oxidizing agents or reducing agents? Well, what is their charge here? It's -1. And what is their charge here? It's -1. Hang on, they haven't been reduced or oxidized. Their oxidation state has stayed the same. And in fact, with chloride ions, they're not a strong enough reducing agent to reduce the sulfuric acid. So if we look at the sulfur being +6 here is also +6 here. So this is not a redox reaction. In fact, the chloride ions have accepted a hydrogen. And what do we call things that will accept a hydrogen? They are acting as a base. So they are acting as a proton acceptor or a base. Okay, so this is actually kind of like an acid-base reaction, isn't it? So the sulfuric acid is doing its job as an acid and giving a hydrogen to that. Now you could, if you want, instead you could um, make this sodium sulfate Na2SO4 instead of NaHSO4. It could just be Na2SO4. And then you just need to have an extra hydrogen chloride and sodium chloride. So you just need to balance it. So that's why I go for this one. But alternatively, you can write Na2SO4 here, but then you're going to end up with 2HCl and 2NaCl. Okay, right. Draw the shape of the Cl3 minus ion, include any lone pairs of electrons that influence the shape. So what we want to do here, we're going to be looking at this. So let's have a little go. Oh my gosh, this one's quite, some of you might find this awkward. Chlorine is the central atom. There's three, right? Chlorine, but chlorine is obviously the central atom. It's in group seven, so it's got 7 electrons because it's in group seven. However, it's an ion, so it has a bonus electron. So actually, this has 8 electrons, but because it's bonded to two chlorines, it's bonded to, it has +2 electrons. I know. These are the bonded ones. And that means there is a total of 10 electrons. So how many electron pairs does this have divided by 2? You're going to get 5 electron pairs. So there are 5 electron pairs hanging around the central chlorine here. Now what we need to realize is that when you have 5 pairs, you're going to be like, you're in that region of being whatever those 5 pairs are called, T-shaped and all of that kind of stuff. So what kind of shape are they going to adopt? Well, we've got 5 pairs of electrons, and how many are lone pairs? Well, you've got 2 bonded pairs and 3 lone pairs. Now, how do I know you've got 2 bonded and 3 lone? Well, we know 3 chlorines joined together, there are 2 bonds between them. So 2 bonded pairs, and the rest must be lone. So we go 5 pairs, take away the 2 bonded pairs, and we're left with 3 lone pairs. So this is what it's going to look like. Okay, the chlorine actually, what you get is, what is this, trigonal pyramidal, what is it, bipyramidal, yeah. So trigonal bipyramidal. Now in the kind of vertical plane, the chlorine atoms will go, that's the furthest these bonded pairs get away from each other. But these bad boys over here, the lone pairs, they're going to occupy kind of like, hold on, let me rub that out. What happens is the lone pairs end up occupying the horizontal plane, which is like where you get the trigonal bit like that. And they occupy like that. So you've got the 3 lone pairs like that. And they're like, that's like a disc going round the middle. And these are in the vertical bit. Now, all we need to do is, instead of showing it like that, we should just do the Mickey Mouse ears, right? So these are like that. They do the electron clouds. You got 2 there and you got 1 there. And there we go. Does it ask us for any bond angles? No, it just says include any lone pairs. We've done that. That influence the shape. We've done that. Beautiful. Right. 5.6. That 1 mark. Oh, what a brute. Right. 5.6 chlorine forms an ion with the group 3 element thallium, Tl. State and explain the bond angle in thallium Cl2 plus. So they tell us that thallium's in group 3. So again, we go, well, Th has 3 electrons normally in the outer shell. However, it is a plus. So actually, there's only 2 electrons around thallium, and it has 2 bonds. So 2 bonded electrons as well that it's getting from the chlorides. So there's a total of 4 electrons divided by 2, ladies and gents, and that gives you 2 pairs. So we've only got 2 pairs of electrons and no lone pairs, no bonded pairs. What kind of thing do you form when you'd like that? Well, you form this thing here. You know the one. It's going to be that, and they are going to maximize their distance from each other, which is 180 degrees. And why are they going to be 180 degrees from each other? Well, because that minimizes repulsion between the electrons. And so that is what we need to put down. So the bond angle is 180 degrees. This is linear. So you don't need to write the shape, but it's linear, or yeah. And the explanation, I don't want to write all that business that I've just put down there on the right about 3 electron pairs. So I'm going to say 2 bonded pairs of electrons. So there's 2 bonded pairs, bonded pairs of electrons. They maneuver, position. I don't know how to word things sometimes. They position themselves as far apart as possible to minimize repulsion between the pairs of electrons. So welcome to Let's Get to the Marks. We're on question 6. It's all that electrode cell potentials. Oh my God, I'd rather slide down a rocky mountain using my organs responsible for spermatogenesis as my only form of brakes than do an electrode potential cell thingy walkthrough. But there we go. It's got to be done. So let's ride that mountain. Question 6. This question is about vanadium ions. Table 3 shows the standard electrode potential values. And so here, these have all been individually connected, these half cells, with a hydrogen half cell so that we can get these electrode potentials. And then they've been put in a little hierarchical order with the larger, greater electrode potentials at the top and the smaller electrode potentials at the bottom, or the more positive at the top and more negative at the bottom. Right. What do these tell us? Well, just generally for your own information, the more negative an electrode potential is, the more likely this is to be the reducing agent and therefore lose electrons. It's going to be oxidized. Now, it generally works that when we set up the electrode potential cell, we put the thing that's going to get, so we make a cell like this, right? This is going to be a crusty GCSE level 3 diagram, okay? No salt bridge or anything, because I'm not interested in that. All I'm interested in is showing you, if I set up my cell, my electrolytes there, my more negative, my anode is going to be on the left and my cathode on the right. I know what you're thinking in electrolysis. Isn't the anode positive? You'd be absolutely right. So it depends on which electrochemical cell you're dealing with. When we're dealing with batteries, the anode is always negative. So get that into your head because you're an A-level chemist now. So the more negative electrode we're going to put here, so like magnesium is the best oxidizer, best at losing electrons. That's going to go there, and then you're going to have your reducing agent, your more positive thing here, which is great at picking up the electrons. Anywho, let's get on with the business. Use the what 6.1. Use the data in table 3 to explain why zinc reduces an aqueous solution of VO2 plus ions to V2 plus, but does not reduce it any further. 2 marks. All right, guys, pause the video. Have a go. Right. I'm going to go through the dreaded explanation of this. So bear with me, okay? Bear with. And what we're going to do here is go, well, look at zinc's half cell. The zinc half cell over here, which is what we're interested in, has a minus 0.76 electrode potential. If we look at the VO2 plus, the VO2 plus is here, and that has a +1. So we can definitely oxidize that. Now, vanadium here, what is the oxidation state of vanadium here, guys? Well, we know oxygen's always -2, so we've got a -4. So the vanadium itself must be +5. So it's reducing, sorry, it's losing electrons to zinc, and it's giving those electrons to vanadium. And look here, once we've got VO2 plus, we know that it's now gone to +4, so it's gained an electron. Then look what happens. It can be further, because that's +34 and this is still -76. This can still give away electrons to VO2 plus and make the VO2 plus VO3 plus, right? It's gained another electron to become +3. And then, because if we go down here to V3 plus to V2 plus, -0.26. So it's still more a negative, and it can give electrons to the V3 plus to make it V2 plus. So we need to put that down, and there's 2 ways you can argue this point, and you need to make sure you know these, because this is a very common question that people lose marks on, and it's explaining why the zinc can reduce those. So what we want to say is the V, and we're not going to go through all of those steps. That would be too much to fit on a few lines. So we're just going to say the V3 plus V, and we're not putting state symbols or anything. We just want to say, look, the electrode potential, oh my days, I'm going to have to swap between using that. Oh gosh, let's go to black. Lovely. Right. Oh my days. Let me thin this out. That's a bit long. Fat, sorry. No, did he? Right, whatever. Right, the electrode potential of the V3 plus to V2 plus is greater. This arrow means greater. What do we mean by greater? It's more positive, the -0.26, than the one for the zinc 2 plus. So we want to say this has a greater electrode potential, or more positive electrode potential, you could write, than zinc 2 plus, than this one. And therefore, that explains why it can be reduced. So it can be reduced by that. Now, the other way to explain it is to work out the EMF. You've heard of EMF. Now, the EMF is the electromotive force, basically the voltage that you get in between any 2 of these half cells. And in order to calculate that, you do the right-hand side let's shorten that down. Oh my days! We're going to shorten that down to RHS. It's basically cathode minus anode, but then you have to remember the difference between electrolysis. So I'm just going to do right-hand side minus left-hand side, all right? And essentially, what we're saying is, that's the negative. So that's the more negative. So this electrode would be my Zn2 plus Zn, right? And this is my right-hand side, therefore, is minus 0.7 six. No, it's not, because what a twit. You see, I've already made that mistake. My left-hand side. So what do I mean by left-hand side, right-hand side? This is the left-hand side, the anode, and it is minus 0.76. I know this is a bit long, but if you bear with me, you can then choose which one you want. So that would be minus 0.76. Now what I'm going to do, my right-hand side is going to be minus 0.26 and is represented by V3 plus to V2 plus. Okay, so that's the way you always set it up. The more positive one is obviously the positive electrode, and the more negative one is going to be the negative electrode. So what we're saying is, can this give electrons to that? Well, we can do this little calculation and find out if it has a positive or negative electromotive force. So we're going to do the right-hand side, minus 0.26, take away minus 0.76, and you can whack that in your calculator now, and you'll see that what you'll get is a plus 0.50. So we can also say the other way we can get this exact same mark is by saying the EMF equals plus 0.5 volts, right? Or 0.50. And that's just to show you how you would work that out in case you don't know. And it can be tricky. There's lots of room for making a mistake here. Bear in mind that this would only get you one mark. And I'll put 2 ticks, but I'm just showing you these are the 2 ways to get the first mark. Now, the actual harder mark is to get the second mark, which is to explain why it does not reduce it any further. And actually, there is an easy way to explain it and a more difficult way, but we're going to go through them both. So where are we? Oh my gosh, have a look, peeps. That's minus 120, and that is minus 0.76. So which one is more positive? So what we want to say is, actually this time, the V2 plus to V, so I want to do this and go V2 plus to V. I want to do it in the same context that I did the first mark, V3 plus to V2 plus. I'm doing it in the same context. I'm saying, look, the other half cell this time, and I want to reverse that and say, look, actually, it has a lower electrode potential, right? The electrode potential of the V2 plus V is lower than the electrode potential, or more positive, if you want to word it like that, than the electrode potential for the zinc. And therefore, it can't be reduced. So basically, that is your chemistry way of saying, look, it can't be reduced because it's giving away electrons more than that. It's more negative. And then we can prove it, slightly more difficult way, we can prove it here. So let me show you how we prove it here. Well, what we do in this situation, we're going to say, okay, so if this can be the reducing agent and be oxidized and pass electrons to the right-hand side, let's test that theory out. Let's go and replace the electrode we have, and we're going to replace it with the V2 plus V. And the V2 plus V over here is minus 120. So let's do that. And now let's smash this into our calculation up here, right-hand side minus left-hand side. So instead of having minus 0.26, minus 0.76 goes to plus 0. Blah, blah, blah. We're going to go right-hand side is minus 1.20. And then we're going to go take away minus 0.76. And if you prefer it to be in brackets, I'll put it in brackets for you. Okay, now if you do minus 1.20 minus 0.76, let's smash that in the calc. And if we get a positive number, then that is possible. So let's go minus 1.20, take away minus 0.76, and we get minus 0.44. So it's a negative electromotive force. It won't happen. This will not happen. This will not pass electrons to that. It will not reduce that. So what you can say is the alternative. You can say the EMF between these cells. Oh my days. What am I writing there? Cheese. Ah! Sorry about that, screaming. It's this, sometimes my fat fingers just hit the wrong things. Right. The EMF is equal to minus 0.44 volts. Therefore, it won't happen. And the EMF is equal to minus 0.44 volts. Now, I should say, I need to make that clear to the examiner because if I just write the EMF is plus 0.5, the EMF is minus 0.44, I want to say this is why it cannot reduce the oh my days, V2 plus to V. So at least I'm clarifying to the examiner what I'm banging on about there. So I can say the EMF is minus 0.44 V, and EMF is always between two half cells, so they'll know what I'm on about with the difference between electropotential and EMF. So don't get these bad boys mixed up. Don't get the E with the little standard symbol, the circle with the line through it, mixed up with EMF. EMF is the difference in voltage between two of these. This is the electropotential, which is the difference in voltage between this and the hydrogen half cell. Anywho, enough whiffle waffle waffle. Let's move on with your favorite topic, electrode cell potentials. Right. Identify the species in the table that can reduce an aqueous solution of E2 plus to V. So we're going to bounce back up here and go, okay, who in this table is more negative than this bad boy? Who's the only thing that could reduce that? Who can give away electrons to this? Remember, the more negative you are, the more you are likely to be oxidized and be a reducing agent. So the only one that is a better reducing agent, better at giving away electrons and reducing things, is magnesium. So identify the species that can reduce an aqueous solution of V2 plus 2V. And now here, oh, geez, this is the mistake that some people are going to make. Everyone's going to get that, right? But some people are going to go, Sugar Ray Leonard, do I write MG or do I write MG2 plus? And only one of these is correct. And I'm going to show you which one you got to write, peeps. So when you're going to write this out, we're going to write these. Oh, well, actually, they're already written. No, they're not. Right. So I'm going to write these out. Look, MG2 plus. Forget the state symbols, right? I'm talking about speed here. So we don't want to do that. What we do is we write out these two halves like this, and you're always going to put the oxidized half on the left here, but we put the more negative one at the top. So this is minus 2.38. And then underneath, I'm going to write V2 plus 2E minus, and I'm going to go to V, and that is minus 1.20. Now, if you write the more negative one above, and then you circle, it's always the right-hand side of that that can react with that. So the magnesium can give electrons away to that. Obviously, Mg2 plus hasn't got any electrons left to give. So it can't be the Mg2 plus that's giving electrons to that. It has to be the magnesium. But this is one way you can always do it. Because if you write the more negative on top of the less negative to see if the reaction's feasible, then it's always the product will always react with the reactant on that side. So you can always do that connection there. So the answer is it's Mg, not Mg2 plus, it's Mg that can do this. And that is going to get you the mark. Mg has electrons to give away to reduce the V2 plus. All right, let's move on. Don't forget, guys, if you're liking the video and it's helping you out understand electrode potentials, you can help me out by hitting the like, right? Obviously, watching your video, watching my videos really helps me out too. But hitting the like, subscribing to the channel, this helps me out massively. All right, helps my channel grow, and yeah. I scratch your back, you scratch mine. Eh? Right, let's move on. Two half cells, Fe2 plus Fe and VO2 plus V3 plus are connected. Calculate the EMF of this cell. Give the conventional representation of the cell. Give a half equation for the reaction that occurs at the negative electrode. 3 marks. So we're going to break this down. We're going to calculate the EMF of the cell and give the representation. So what I'm going to do is draw my little thing out over here. Okay, again, don't worry. I know I should have a salt bridge and all that business. Remember, the more negative one is going to go here. The more positive one is going to go here. Generally, that's how we're going to do it. So we scroll up to the tables and we say, what is V2 plus and what is VO2 plus 3 plus? So we go, VO2 plus 3 plus is plus 34 and the iron is minus 44. So did I get that right? Plus 34 for the, yeah, I did. Right. Okay, let's zing back down. Plus 34. Oh my gosh, I've forgotten it already, folks. Help me. The iron is minus 44, and that is plus 34. All right. Bosh, bish, bash. So, the iron was minus 44. Why am I saying minus 44? You know what I mean. It's just my brain can't hold information for very long. Minus 0.44. And over, we're going to put the positive one over here, which is the VO2 plus V3 plus. And I believe that was plus 0.34. So remember, if I want to calculate EMF, I'm going to do the right-hand side minus the left-hand side. Now that's the general rule, but that can get you in a stick with that with the first step of this question. When I was trying to prove that one wouldn't go with the other, you can prove it by flipping those. Anyhow, enough of that business. What I'm saying is the right-hand side minus the left-hand side. So we're going to go 0.34 minus 0.44. And what you're going to get when you go 0.34, take away minus 0.44, that basically minus minus becomes a plus. So we're going to get an EMF of 0.78. So 0.78. Another. Oh my God, I'm fiddling around. I've deleted everything. Oh gosh, here we go. Right, cell representation. What are they on about cell representation? Well, they're asking you for the conventional representation for this cell. So it's how we draw it all out. We have to include electrodes, salt bridges, all the elements here. Thing with the VO2 plus V3 plus, you can't see here, but if we zing up to the VO2 plus V3 plus, you'll see that hydrogen is also involved. So we have to include hydrogen ions on that as well. So what we're going to do is write this out, and what you're going to do, this is the negative, the anode, and over here we've got the cathode. This is all happening there. This is the more a negative electrode potential. So this goes on the left-hand side. And just like you would draw out the cell, this would go on the right-hand side. Okay, so we start on the left, but here's the thing. For both of the electrodes, we put the oxidized form on the inside in the conventional representation. So what we do like this is we're going to go Fe, and it's solid. Now we are going to put a line here. This line, by the way, represents a change of state. This is called a phase change. So we're going from solid to aqueous. So change in the phase. So we're going to call that 2 plus. We're going to slap down the old AQ. That is the oxidized form, the form that has lost electrons. And then in between, we're going to put a salt bridge. Now, back in my day, we used to use two dotted dashed lines. Now we use two solid lines for the salt bridge. Okay, what's next? Wiffle, waffle, waffling. Now we need to write this one. What's the oxidized form? Is it V3 plus or is it VO2 plus? Well, that is minus 2. So that has 2 plus charge. That's minus 2. So this must, that's plus 2, minus 2. Oh my God, I can't work up my brain. That's plus 4, that's plus 3. Okay, so the oxidized form, the form that has less electrons of vanadium is this form. This would be a plus 4, whereas that is plus 3. Okay, so we're going to go VO2 plus, and that is aqueous. Now, here's a little thing. We've got to include that hydrogen ion. Now, what you do here, because the hydrogen ions obviously are aqueous, ions are always aqueous, we are going to slap that in here, and we're going to put AQ here as well. And so when you're in the same phase, and aqueous is the same phase, you just put a comma to separate them. So now I'm going to put V3 plus AQ. You're like, yeah, baby, are we done? Not quite yet. Because these are aqueous, we can tell over here at the anode that the electrode is the ion because it's solid. But what are you going to use as an anode, as the cathode? Because you haven't got a solid electrode to conduct electricity into the electrolyte here. So what we have to do is put a vertical line there, and then we're going to put the what the electrode's made of, and it's made of platinum. Now that always comes last, regardless of what's on that half of the cell. The electrode comes last. Now, if we've been using Fe3 plus or Fe2 plus, sorry, and Fe3 plus like that, they both would be in aqueous. We would put the PT for platinum here. So it is a potential, if you've got two solutions on either side, that you would have a platinum electrode on the left and on the right, but they would be on the outside of the cell diagram, basically. So you put your platinum there for these, but these guys have got an iron electrode, so we just include that there. Anywho, that should be all of the marks, all of the marks, all of the marks. Right, there we go. Now, half equation, easiest bit. This is more GCSE. Give the half equation for the reaction at the negative electrode. So we're just looking for, at the negative electrode, it's losing electrons, it's being oxidized. State symbols might not count here, but we're going to slap them in anyway. And that is the half equation for oxidation at the negative electrode at the anode. Okay, guys, let's move on to the last part of this question. Well done if you got all of that right. Boom! Question, right? So let me just smash out the last bit to this question. Let's just shrink that down. Percentage purity. Okay, so we've got one of these bad boys, a bit of an amount of substance, but it's going to be, it's kind of a bit like a, oh, what do they call them? Reverse titration, back titration type thing. It's similar to that. So we've got 0.15 grams of impure ammonium, whatever the hell that is, vanoxide, whatever that is. Okay, I can't work that out. So 0.15 grams of that, and it's impure. It's added to dilute sulfuric acid to form a solution containing VO2 plus ions. The VO3 minus ions, all of the VO3 minus, you might say, well, what is the VO3 minus? Well, the VO3 minus is in here, right? So all they're doing here is telling us that all the VO3 minus ions are converted to VO2 plus ions. So it's a one-to-one. Okay, that's a one-to-one. These VO2 plus ions are reduced to V2 plus by the reaction with excess zinc. And we can see that here. The VO2 plus, remember, that's one-to-one-to-one. So that represents that in our molar ratios are being converted to V2 plus. And look, that's 1-to-1 because there's a coefficient of 2 and a coefficient of 2. So I know that that is 2-to-2, and that's going to come in handy later when you do the question. The excess zinc is removed by filtration and washed. Thanks for that. So the zinc is chucked away. They just add this stuff in, like, why do we actually need that? The filtrate containing the V2 plus ions is titrated. So, right, so all of this has been converted to that. They get rid of the zinc, so we're just left with the vanadium, aqueous, and water. This filtrate with the vanadium ions is then titrated with a 0.02 mole per decimeter. Identify what that is. That's the concentration. Circle it, highlight it. Solution of acidified potassium manganate. That means we've got hydrogen ions knocking about 29.43 centimeter cube. What is that number? That is volume of solution I needed to oxidize all the V2 plus ions to VO2 plus ions, right? So they then go further, and you can see the ionic equation for the reaction of manganate ions with V2 plus is here. So we've got manganate with the V2 plus. Check out, we've got a ratio 3-to-5. Okay. Calculate the percentage purity of the ammonium, well, the NH4VO3, because I don't want to pronounce it because I can't work out what it's called. Give your answer to 3 significant figures. Guys, you know, I'm going to say, pause the video, get your pen, get your paper, get your calculator, have a go at this one. Yeah, let's go. All right, I'm going to go through the answers. So, like, you've got all that big fat stem. It's like, where do I start? My thing is just, okay, I'm in my exam. Breathe. I've done my work to go through this and highlight and scribble on it. I know I've got C and V, so my starting point is N over C times V. And I'm just going to not panic about all this complexity. So I want to convert that to decimeters. So I essentially, the first part, I want to do the concentration, which is 0.02, and I want to times that by 29.43. But remember, it's chemistry. We got to use volumes in decimeters, not centimeters. And before I panic, I can get this, and I know that I'm on the scoreboard. I'm going to get some marks. So what do we get? We get 0.0005886. So 0.0, I'm going to have to double check that. And you should double check your working. And you could, of course, do 5.88 times 10 to the, or 5.89 times 10 to the minus 4. But let's just make sure I've got that right. So let's go 29.43 divided by 1,000 equals that times 0.02 equals, yes, that's correct. So you might want to do, I don't know whether you want to start rounding at this stage. Personally, you should keep it all like that, but you might be someone who wants to start rounding, you know, and call it 5.89 times 10 to the minus 4. That's all good. I'm sure it's all going to be acceptable. That's a 6, by the way. I don't know what that looks like. Oh my days, I've made that worse, haven't I? Oh, geez. Right, let's move on. Right, before we move on, I want to write down, this is definitely moles, but I want to write down what it's moles of. So I go back up here and I look and I study and I go, oh, it's of the KMNO4. So this is of the manganate ions. Now, it doesn't matter whether you write KMNO4 or manganate ions. We're looking at the same thing here, peeps. And then I know that this is in a 3-to-5 with the V2 plus. So it reacted in a 3-to-5 with the V2 plus. And look, that's my link. The V2 plus is my link between the two equations. It's the same thing you do in a back titration. So let's convert this from 3-to-5. So the ratio, oh my days, is 3-to-5. So how do you handle that as a calculation? Divide by 3 times by 5. So you always divide by the first times by the second. So once you know the ratio, so I'm going to divide by 3 times by 5, and I'm going to have more of the V2 plus. So my V2 plus moles are equal to zero point 0.0. Oh my God, why am I writing 0.00981? So now what do I want to do with this bad boy? Now that I've got that, oh my gosh. Right, I've got the V2 plus 0.000981. Is that right? Should double check on my calculator. Got to do loads of checks here. Now I've got the link of that to that. No, you don't need to go 5 to 2. That is the V2 plus that's there. So now we come up here and we go, oh, hold on a minute. If I have 0.00981 of that, then I've also got 0.000981 of VO2 plus, because it's 2 to 2. And then it said these VO2, all of the VO3 minus were converted to VO2 plus. So essentially that's a 1-to-1. So I now know I've got 0.00981 of the ammonium. Oh my gosh, I should have learned the name of that, right? The NH4VO3 is also that, because look, it's all 1-to-1 going up here because they told us basically explicitly. So we only had to do that one ratio, which by the way, that would have got us a mark. So this would have got us a mark. Ratioing would have got us a mark. And so we got at least 2 marks for getting down to there. Now we're working that all the way back to there. Now what do we need to do? You know the coup. You might get stuck here, but now you know the moles of that. You can work out the MR, and you know what we're going to do. We're going to do mass over MR times moles. And why are we doing this? Well, because they're giving us 0.15. And remember, we're going to do purity. So percentage purity, how pure is it? Well, we're looking at 0.151 is the impure. So I want to divide the mass by that and times 100. So I need to know the mass of that I have. And if I work that out, then I can divide it by that times 100. So if I get a mass now that's bigger than 0.51, you get what I'm saying, bigger than that. It can't be. I can't have more of that than there is in the impure of that. It's impossible. All right, let's do the MR. I think if we add this up, what, 14, 4 hydrogens, get the vanadium, get the oxygens. I think this is, oh my days, is it 100 and, I think it's 126. No, it's not 126. It's 116.9. So I'm going to times that by 0.0000981. And that is going to give me 0.114679. And that is grams. Okay, now all I need to do is divide that, as we said up there, by 0.51 times 100. Let's see what we get. Da, 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 da. Oh my days. Sorry, folks. Da, 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 da. I'm messing around here. Okay, I don't know what you guys got, but I don't know what you got in your calc. I tried to leave everything as it was, and I got 75.94. They have said 3 sig fig. Um, yeah, I know what they're going to do here. They're going to accept either 76%. It's not what I would do, but you would have to write 76.0. Myself, because that is less than 5, I would leave it as 75.9. That's just me. But on the exam board, that's in the allow section, 75.9. That is what I would do as 3 sig fig. I wouldn't take it up to 76.0, but they like either. Okay. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video. Okay, welcome to Let's Get to the Marks. Going through a nice KW question for you. This is from the A-Level Chemistry AQA Paper 1 2024. Let's get into it. So, question 7. At 40 degrees, the ionic product of water KW is equal to 2.92 times 10 to the minus 14 mole 2 DM minus 6. Give the expression for KW. Calculate the pH of pure water at 40 degrees. Give your answer to 2 decimal places. It's worth 3 marks. So let's do it. Why don't you pause the video, see if you can work this out, and then unpause and I'll go through the explanation. Okay, so let's go through it. Well, KW is equal to OH minus times H2O times H plus. I'm messing myself up there. Okay, now when it says pure water, this means it's only made of H2O molecules, and each H2O molecule is made of an H plus an OH minus. One thing we know about these two bad boys is that for every water molecule, there has to be one H plus and one OH minus. So you have to have an equal amount of hydrogen ions and an equal amount of hydroxide ions when you're looking at pure water. So what we know from this is that KW, you can simplify this, is equal to H plus squared, because we're basically assuming that these are equal. So it's like squaring H plus. So now we want to find the pH. So what we're going to do is go, well, if 2.92 times 10 to the minus 14, which is our KW, is equal to H plus squared, then what we want to do is get rid of the square so that we just isolate H plus on itself. So we're going to square root 2.92 times 10 to the minus 14. And that is going to leave us with H plus. And this will get you your first out the two wonderful marks. So let's do that first of all. Bada bada bing, bada bada bang, bada bada bing, badang badang bang. Okay, yeah. So if you square root 2.92 times 10 to the minus 14, you get 0.00000001708, which is just roughly 1.7 times 10 to the minus 7. You might want to round that to 1.71 times 10 to the minus 7. Look, stick a little 1 there if it makes it more accurate. And then you just minus log that, which is the hydrogen ion concentration, and you're going to get the pH. And when I do that, diddly-dee, minus log answer, I get 6.767. So we want to go 2 dp, and I get a pH of 6.767. So I'm going to round that to 6.77 like that, because that, yeah, I round that to 6.77. There you go. Let's zing some marks in there. Right, let's look at this next part to the question. 7.2, 35 centimeter cubed of 0.150 mole per decimeter aqueous sodium hydroxide are mixed with 20 centimeter cubed of a zero point 0.1 mole per decimeter solution of hydrochloric acid. The temperature of the solution formed is 40 degrees. Calculate the pH of the solution formed. Give your answer to 2 dp. Oh my gosh, I'm going to sneeze again. Oh, geez, there's colds going around and I'm struck down, people. The dirty viruses have got me. Okay, right. What do we need to do here? Well, let's write out an equation. It looks just like sodium hydroxide and hydrochloric acid. We all know that's like the kind of easiest equation in the history of chemistry, isn't it? That one. And that one is just like that, plus H2O. So just your straightforward one. It's 1 to 1 to 1 to 1. We love it. Now we've got a volume and a conch and a volume and another conch. So we know we're using N over CV. Let's go ahead and work out how many moles of each of these we've got. So for sodium hydroxide, I've got 0.035 decimeters. That's my volume. Why am I changing it to 0.035? You should be able to do that by now. You just divide by 1,000. Then I want to times by the conch, which is 0.150. And that is going to give me 0.00525. Got a bit excited there with the amount of noughts. So that is my sodium hydroxide. Now, how many moles of hydrochloric acid have we got? Well, we've got 0.02. I don't know if I said pause the video and have a go, but that's what you should do before doing this, because it's a big fat 5 marker. And that is going to mean I've got 0.002 moles of HCl. Now, bearing in mind they react in a 1-to-1, which one are we going to have left over? Well, this we're going to have 0 after the reaction. That's going to have 0 left. This is still going to have 0.003 0.25 moles left. Let's go ahead and work out the concentration of the sodium hydroxide that we've got left. So what is the volume? Now we need to combine the volumes to make 55 centimeter cubed. And if we do N over V, we're going to get C. So I'm going to do moles of sodium hydroxide over 0.055. You're starting to get the hang. You generally just add two noughts in front when you want to convert. And if we do that, bing, 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 bada, bing, 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 let's do that. 0.00325 divided by 0.055. That gives me 0.0590. Oh, that gives me, yeah, 0.0590. Now know that my hydroxide ion concentration is equal to 0.0590. What do I need to do next? Well, it did tell us here that it's at 40 degrees, and we know this one up here was at 40 degrees, so we got the same kW. So this time we know that kW, in fact, we don't have to write it as kW. We can just write it as 2.92 times 10 to the minus 14. What was that equal? That was equal to the hydroxide ion concentration of 0.059 times the hydrogen ion concentration. So now how do we rearrange that to find H plus? Real simple. We're going to do 2.92 times 10 to the minus 14, divide both sides by 0.059. And we're going to end up with that as our H plus ion conc 0.94 I've got, and that is times 10 to the minus 13. You might want to keep all the numbers in your calculator. I'm just getting tired of writing it out. So that is my hydrogen ion concentration. So if you want to find the pH, just press minus on your calculator, press log, a bracket will come up, enter that 4.94 times 10 to the minus 13. And then all you need to do, let's try that, answer equals 12.306. So my pH is 12.306. Check how many sig fig. It's not sig fig this time, it's 2 dp. As that is bigger than 4, we're going to round that up to 12.31. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Okay, welcome to Let's Get to the Marks. This one is on the Born Harbor cycle and yeah, perfect ionic model, that type of thing. So what you should do is at the start of each one of these questions, this is A-level chemistry, by the way, in case you clicked on this thinking it's GCSE, pause the video at the start, get your pen, get your paper, get your calculator, have a go at the questions as I go through them, and then unpause the video to watch the explanation. All right, so the first question up is 8.1. Theoretical values for enthalpies of lattice dissociation can be calculated using a perfect ionic model. State the meaning of the term perfect ionic model. Pause the video. Okay, I'm going to go through the answer. So perfect ionic model, it means that you assume the ions are perfect spheres. You can use the word point spheres, so they are perfectly spherical, or that they have no covalent character. So that they're perfect ion spheres with a distance between them. They don't have a shared pair of electrons or anything like that. Okay. Let's move on to the next part. So we got 8.2. Enthalpies of lattice dissociation can also be obtained from Born Harbor cycles. Here we've got the Born Harbor cycle. Here, complete figure 3 by writing formulas including state symbols of the appropriate species on each of the two blank lines. Now you might be thinking, what are the two blank lines? It's this one here and this one here. Why don't you grab a pen, grab some paper, have a go? Pause now. Okay, I'm going to go through the explanation for you. So what we're going to do, right, what have you got down here? You've got Na2O. What is that? That's solid. That's sodium oxide in a solid lattice. So what we want to do is write the formation of that. And the formation of that is going to come from the elements in their standard states. So we're going to need two NAs. And what are they going to be? Solid. Sodium is a solid. We're going to add that to oxygen, right? And oxygen is gaseous. But have a look, folks. The standard enthalpy of formation is for 1 mole. So Na2O is 1 mole. So actually, I can't have O2. I have to have half an O2 in order to make 1 mole of Na2O. It's not that you need 1 mole of the constituent elements. You need 1 mole of a compound formed from its constituent elements in their standard states, but that's saying 1 mole of the compound. It doesn't mean you need 1 mole of the ingredients. It means you make your amounts of ingredients to suit the 1 mole of the compound. Anyway, enough whiffle waffle. Let's do this equation up here. So have a look at the one before. So the one before shows us two sodium gaseous. That means they've already been atomized. Sodium has already been turned into gases. Oxygen, have a look. The O has a G next to it. It has been atomized. It no longer says O2. So the oxygen has also been atomized. So what's the difference? We go up here, look over here, Na plus. Okay. So what has happened is the sodium has been turned into sodium positive ions. So I just need to write this out again, but make those sodium positive ions. So 2Na plus. Uh, yeah, I should probably keep this state symbols, otherwise I'll get in trouble. And then we've got the O. Now the O has been atomized, but not been ionized yet. It's not received an electron to become negative, what we call the electron affinity. So, and how many electrons will there be in, well, there'll be two, one from each of the sodium ions. Now, notice you might be saying, but sir. Oh, geez, you might be saying, sir, you idiot, you haven't put a plus there next to the Na. There we go. Right. Now, you might be saying to me, sir, how do I know that the O isn't becoming a negative ion there, and then the sodium ions are ionized here? How do I know this isn't the electron affinity for oxygen and then the sodium ions ionized here? Well, because if you look down here, we can see that there were two electrons, and then the oxygen here, this is where the oxygen picks up its first electron, hence there's only one left of those two. And then over here, the oxygen picks up two electrons, hence there's no electrons left. So we needed the formation of those two electrons first of all. And here you see it says 2Na plus, so the electrons must have been released up there. Anywho, that's going to get you two beautiful marks like that. And let's move on with the questione. So let's zing down here to 8.3. Table 4 shows some enthalpy changes. Here's table 4, enthalpy change. We've got the delta H per kilojoule mole. Enthalpy of atomization of oxygen. You can see all of those. I'm not going to read through them all for you. Use the data in table 4 to calculate the enthalpy of lattice dissociation of sodium oxide. So what you need to do is use these numbers and place these numbers on here in the appropriate place. And then you can work out the lattice dissociation. What have we got to work out, actually? It would be nice. We're working out the lattice dissociation of sodium oxide. Now, let me tell you something here. The lattice dissociation is, this is the lattice, Na2O, and that is the arrow going up to the ions in the gaseous state. That is lattice dissociation enthalpy. The energy, the enthalpy or the energy change when 1 mole of a compound in a lattice, you see what this ionic compound here, is turned into its ions in their gaseous state. So that is the lattice dissociation enthalpy. You cannot calculate that directly from this Born-Haber cycle. What you can calculate directly from the Born-Haber cycle, this is a key point, you can calculate this enthalpy of lattice formation. So this is the formation of the lattice from its ions in their gaseous state. We can calculate the blue line. All you have to do is reverse the symbol at the end. I had to mess about and get all of this on here at the same time, as you can see, so that we can actually see what we're doing, which was a little bit of a pain there. So just bear with me for a second, all right? Now, what we're going to do, we're going to write these numbers in. So we've got the atomization of sodium. All right, guys, let's write all these blooming numbers in. Yep, I've got all these numbers up. That took me a little fiddling and fiddly. Let's start with the first one. They tend to go in order, but not always. So what I mean by that is enthalpy of atomization of oxygen. We're going to work our way clockwise around. I can't speak. So we're only doing half an oxygen molecule and we're atomizing it to that. So it's just 1 times 248. 248 went in to turn it from O2 into G. And I know what you're saying, but isn't half O2 already O? No, it means half a mole of O2 molecules, right? Turns into a mole of oxygen atoms. So you still need to break all those covalent bonds there. All right, let's move on. The next one is the enthalpy, the atomization of sodium. So if you're wondering, look, it goes in order. So I haven't got a study too hard, 109. There is a catch here, guys. Look, the atomization is when you form 1 mole of gaseous atoms. I'm forming 2 moles, so I need to times this by 2. So we're going to times that by 2. All right, let's look at the next one. The next one is the Oh, it's not in order. The enthalpy of formation of sodium oxide is minus 416. So that's down here. Okay. So how do I know this is the enthalpy of formation of sodium oxide? All you've got to do is use your definitions that you've learnt off by heart or on revision card. So the formation of 1 mole of a compound from its elements in their standard states. Okay, and that is minus 416. Now we're going to go to the first ionization of sodium, back on track, peeps. That's this one here going up here, and that is plus 49 whatever, 494. So that's the first ionization energy, or first ionization of sodium, plus 494. But how many moles of ions do we form? That is when 1 mole of gaseous ions are formed from their elements in their gaseous state. Now we have the element in its gaseous state, but we have 2 moles and we're forming 2 moles of sodium ions. So guess what, peeps? I need to double bubble that one. And then what we're doing here, where were we? Where were we? The first electron affinity of oxygen is going to be minus 142 to add 1 electron. And then to add the next electron is positive. So plus 844. And then we have our mystery, our unknown, our lattice dissociation. But to be honest with you, you cannot work that out from this. You can work this out, and this is our enthalpy of lattice formation. And then from that, we can work that out. So what are you going to do? Well, what this diagram shows you, the Born-Haber cycle, is that this bit here is equal to all of that. So we can set that out on an equation like so. So we can work out from this that minus 416 is equal to that, all of this. And therefore, minus 416 simplified by adding all these together equals 2156 plus x. Let's take away 2156 from each side so that we can actually isolate x and make it the subject. And we're going to find that we have 2572 is equal to x. And as we're taking it away, it's going to be minus 2572 is equal to x. But x is that, and we want to calculate that. These are exactly the same, except for you reverse the symbol. So actually, our final answer is that the lattice dissociation, we've calculated the lattice formation. So the lattice dissociation enthalpy is equal to plus 2572. And that is going to get you all of the 2 marks. All that effort for 2 marks. What a pain in the ass. Now, there is another method for this, and I did a live on this quite recently, one of my Monday night chemistry A-level lives. And if you're interested, click the link up there and you'll see I go through both methods and I do countless examples of the Born-Haber cycle that you can work through. And as I say, just click the link here to watch that live. And I go live every Monday for chemistry A-level, so feel free to tune in. All right, guys. Let's go. This question 8.4 says, explain why the second electron affinity of oxygen has a positive value. Check it out now. Check it out now. Check it out now. So what they're saying is, look, this one is negative. It was minus 142, and this was plus 844. So hold on a minute. We're getting an exothermic reaction. Oxygen wants to become a negative ion. Of course it does. It wants a full outer shell. Then why do we have to put energy in to force that last electron in? And the idea is you're trying to add an electron to an O- ion, so there is repulsion to be overcome. So what we want to say is we are adding an electron to an O- ion, so there is repulsion to overcome. All right. So yeah, there we go. Coolio. 8.5. Time to come alive. 8.5. Explain why the enthalpy of lattice dissociation for sodium oxide is greater than the lattice dissociation of sodium chloride. So let's pause the video, grab your pen, grab your paper, have a go, or I'm going to go through it. Right. If you think about it, sodium chloride is made of a sodium positive ion and a chloride ion. And sodium oxide is made of, well, it's two sodium pluses, isn't it? And an oxide ion, which is two minus, it's in group six. So our first point is that the oxide ions are -2 compared to -1 with chloride. And then also the second point is the oxide ion is smaller, so has a higher charge density. Okay, and so both of these factors combine. Essentially, what we're saying here is sodium with its positive charge, and it's going, "Come to me, baby." And the oxide ion is like that, but the chloride ion, the negative charge, is spread over a bigger distance. And so this here is going to have a greatest lattice dissociation enthalpy. It's harder to break that than it is to break that. Okay, right. And we've explained that there. All right, you can see that. Let's move on. 8.6. Time for a bag of tricks. All right, enough of the stupid rhyming. Sodium chloride dissolves in water. Table 5 shows some more enthalpy changes. Here's the enthalpy changes. We've got the enthalpy of hydration of chloride ions, -364. We've got the enthalpy of hydration for sodium plus ions, -406. We've got the enthalpy of lattice dissociation for sodium chloride, and that is +771. Use the data in table 5 to calculate the enthalpy of solution for sodium chloride. There are plenty of ways to do this. I'm going to show you how I do this, but it might not be the way that you want to do it. But that's just it. So what I'm going to do, what we're talking about here, guys, we want to know about the enthalpy of solution for sodium chloride. So could you write the equation for that? You might get that in a separate question. So you should be able to write the equation. So the enthalpy of solution for sodium chloride means take sodium chloride, add it to water, okay, and make a solution. So dissolve that lattice, make a solution, and what you're going to get, you should get, is sodium ions, aqueous. So it tells us solution. So don't be worrying about it being gaseous or anything like that. It tells you the enthalpy of solution. So what we don't know is this. We don't know this enthalpy of solution in kilojoule per mole. How can we work it out from this data? Well, we've got the enthalpy of hydration of chloride ions. Again, this tests you. Do you know what that is? What's the definition? It's from its gaseous state. So that's the difference. We're going from gaseous to there. So to go from gaseous to there to aqueous, so enthalpy of hydration to solution is -364. Now, I don't need to multiply by any coefficients. You can see this is all balanced up. So now we're going to do the enthalpy of hydration for sodium ions. And the enthalpy of hydration for sodium, the only difference here is these are gaseous ions, and it is -406. Exothermic, they obviously prefer to be in solution, don't they, than to be gaseous, obviously. And then over here, we got the enthalpy of lattice dissociation for sodium chloride. What is lattice dissociation? It's when 1 mole of a lattice, AA, we've got 1 mole there, is broken down into its gaseous ions. So that is what lattice dissociation is. So we're going to break this down into its gaseous ions. And if I could go up to the Born-Haber cycle, that's what we calculated. But it being, I've already got these ions down here. Why am I drawing them out again? There's no need. But I've kind of like, it's kind of like not the best looking one, but neither am I. So there we go. Right. Let's smash this together. That is +771. So we've got our enthalpy. To work out the direction of the arrow is important. You might say, why isn't the arrow going up? If they had given me the enthalpy of lattice formation, then I would go from the ions and the arrow would be going up there. But they've given me the lattice of dissociation. So I could work it out from either, but the symbol would be -771 and the arrow would be going up this way if it was formation of sodium chloride, the lattice. Okay, but it's dissociation. So Just like with Hess's law, this technique some of you may have done, you draw an arrow, a big arrow going round once you've drawn your cycle, and you draw some arrows on it, and anything that goes against the arrow, we reverse the sign. Is this going against this arrow? No, they're going together. So I'm keeping them as plus 7, 7, 1. Then I come here and I go, this arrow's going up. Is that arrow going up? Yes. Is that arrow going up? Yes. So I just keep these exactly as they are. There's no changing of any symbols, no multiplication because there's no coefficients. Smash these all together and your answer is going to be 1 kilojoule. Yeah, why am I writing the units out? They've already got it here on the answer. So the answer is 1. Hopefully that doesn't look like a 2. I don't know what that looks like, but the answer's 1. There we go. Okay, what was that? 2 marks? Bish bosh. Gosh, I'm getting tired. This is some long question. This has been a long paper. Okay, 8.7, give a reason why data books do not contain a value for the enthalpy of solution of sodium oxide. So essentially this one is one of them little tricky ones. You'd be forgiven for getting this wrong, but you might say, oh, why is there no value for the enthalpy of solution of sodium oxide? And the reason is because if you remember from, if I bring this back, when I did the enthalpy of solution of sodium chloride, you go sodium chloride plus water. What happens if you do sodium oxide plus water? You actually form sodium hydroxide. So what we want to say is it reacts with water to form sodium hydroxide. So that is the reason why. Now we get to calculate the temperature in degrees at which this reaction becomes feasible. It's the last part to the question. And yeah, we just got to calculate the temperature at which this becomes feasible. So why don't you grab your calculator, pen and paper and have a go at this one? Or I'm going to go through it. So this is kind of going off topic a little bit, where it's a bit of entropy mixed in here. And there is an equation that you have to know. And so if you need to calculate the temperature, um, simplifying from the overall big fat equation on entropy and enthalpy, you can just do that. The temperature is equal to the enthalpy divided by the entropy at which this will become feasible. And so all we need to do is substitute our numbers in and go plus 411 kJ. Now there's a reason why I'm writing the units, as you will see. And then we're going to divide that by the entropy, and the entropy delta S is plus 90. Now this can be confusing on the eyes, so it's worth practicing these. That's why these are always good. You got a J and a K. You might be thinking, oh, that's like kilojoules. It's not. This is joules per Kelvin, right? Per unit temperature of Kelvin. Now, what have they asked us? Wait, let's spot it, peoples. They've asked us in degrees, and also we've got this issue here. Otherwise, this is quite straightforward. The energy is not the same. So what you're going to do, oh my gosh, what you're going to do is you're going to go 411, and in order to convert joules into kilojoules, I'm going to do 90.1. And I guess you could divide by 1,000, or you could just by times by what are we doing? Times 10. Yeah, I could just divide by 1,000. That'd be easier. What am I saying? Times 10. Oh my God, times 1 times 10. I've lost the plot, peeps. I've lost the plot. Times 1 times 10 to the minus 3. Oh, you could just divide by 1,000. That would have been a lot simpler, wouldn't it? Never mind. Right, and then if we do that, boys and girls, we get 4561.6. Now that means the joules have cancelled out, and that is going to be Kelvin per mole. Now it asked us in for degrees, so we need degrees, right? So oh, it's not even going to be per mole. The moles have cancelled out. The energy units we've made the same have cancelled out. So the only thing we're left with is Kelvin. And what we want to do is turn it into degrees. How do you turn Kelvin into degrees? We are going to take away 273, aren't we? If I had naught and I wanted to turn it into Kelvin, it'd be minus 273. So I need to minus 273 to turn my Kelvin into degrees. And we're going to get 4289. Gosh, that was a long question. I won't say anything that will get my video banned. All right, guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next vid. Take care. Okay, guys, question 9. Let's get into it. It's about metals and their compounds. So let's go. Question 9. This question is about metals and their compounds. 9.1. State why the atomic radius of calcium is greater than the atomic radius of magnesium. Okay, why don't you pause the video, see if you can do that in your head or scribble it down, and then unpause and watch the explanation. All right, here's the explanation, guys. So if we look at magnesium, it's got an atomic number of 12. This means it has 12 electrons. So if we draw out magnesium, what have we got? One, two. Oh, you get the idea. I can't be bothered to do that. Let's do it like this. Mg, right, has what, 12 electrons. So 2, 8, 2. A lot better than watching me struggle to draw rings and stuff like that. So that's the size of magnesium. Let's check out the size of calcium. 2, 8, 8, 2, and that's because calcium has an atomic number of 20. So you can see it has an extra energy level and therefore it's larger. So we just need to say Ca has an extra energy level. Obviously, it's in another period, it's down the group, so it's larger. Right. 9.2. Magnesium reacts with steam. Give an equation including state symbols for this reaction. So magnesium with steam, you have to know this one off by heart. So what I suggest, if you don't know this and you're scratching your head, get it on a revision card and learn it off by heart because it's one of those one markers that comes up sometimes. So you want to do Mg plus H2O. Now, we need to do state symbols because it says so there. So steam is a gas, not a liquid. So it's slightly different than if you do Mg plus H2OL. This is a gas. So you're going to get magnesium oxide. It comes out like a white vapor or a white smoke. You also get solid, obviously, magnesium oxide, but you might see a little bit of white smoke as well. And you're also going to make, on top of this, what is going to be released? Hydrogen. Yeah, because if you think that Mg has nicked the O, that leaves H2. And that is going to be like that. Beautiful, 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 beautiful. Right. There we go. So extra energy level and hydrogen gas release. Let's move on. We've got a 3 marker. Similar sized pieces of barium and magnesium are added to separate 100 centimeter cube samples of dilute sulfuric acid. In each case, the sulfuric acid is in excess. The barium reacts quickly at first. After a few minutes, the reaction stops, even though there's still some unreacted barium in the flask. Now, we can't say it's because the sulfuric acid has run out. They've told us that reactant is in excess. Okay, the magnesium reacts more slowly than barium, but the reaction continues until all the magnesium has reacted. Explain why. Right, and these are the 2 hints for this question for 3 marks. So explain why the barium initially reacts more quickly than magnesium. So why does barium react more quickly? The barium reaction stops before all the barium has reacted. Why don't you press pause on the video, grab your pen, grab your paper, have a go. All right, I'll go through the explanation for you. So why does the barium react more quickly? Well, let's take a look at barium and let's take a look at magnesium. So we're going to need the periodic table for that. Let's check out where magnesium is. Magnesium is here, right? So magnesium is 282. And let's check barium out. Whoa! Barium is 56. I'm not going to draw all the box orbitals out for barium because we know the old 282 doesn't work. But you can tell barium's valence outer 2 electrons are way further from the nucleus than with magnesium. Barium outer shell, we could say valence, but outer shell electrons are further from the nucleus. So feel less force of attraction between outer E minus and positive nucleus. I mean, this even outweighs the increase in nuclear charge because barium has a greater atomic number. It's got 56 compared to 12. So it has way more positive charge in its nucleus, but that's outweighed by the distance. We could also add as well, if we wanted to just go extra, and I don't recommend you do this, but barium has more shielding. So what does that mean? There are more shells between the outer electrons and the nucleus. So again, it feels less force of attraction. So essentially, it's going to lose those electrons more easily and therefore more easily form, what do you call it? Right, more easily react. Okay, what else do we need to do? So we've kind of explained that. Give us that take. The barium reaction stops before it's reacted. Right, let's look at the barium reaction. Okay, so we've got Ba, and we could write this as we got what? Ba solid. And what happens when barium reacts with sulfuric acid? You might remember what the test for sulfate ions is. The test for sulfate ions, we add barium chloride, don't we? And essentially you get Ba2 plus reacting with the SO4 2 minus. And that's exactly what you've got going on here. So we're going to make BaSO4. And this is going to be a precipitate because we know this is what they use in medicine in barium meals because it absorbs X-rays and it coats your organs. This is going to give us clues in how to answer this quite difficult application question. So let's have a little looky at what's happening here. So why is it that after this initial quick reaction, it doesn't react, whereas magnesium gets used up, obviously, because the sulfuric acid's in excess, so that's why the magnesium gets used up. But what happens here? Well, we form barium sulfate, and what actually happens is the barium that's still left that hasn't reacted yet with the H2SO4 gets a layer around it. Let's pick a different color. What do you reckon? Let's go with green. Um, I mean, barium sulfate's white, so there we go. But I'll use green because white's not so cool. Right. So if this is the BaSO4, now remember, you know from your knowledge about barium meals that barium sulfate like lines the organs and things like that and lines the digestive system and so therefore absorbs X-rays and can highlight stuff during medical imaging. Well, the barium sulfate actually coats any remaining barium metal. So before it can react with any of the excess sulfuric acid, it coats the existing barium and the excess sulfuric acid particles actually cannot get to the barium metal to react. And then we just need to put this in words to get our final mark. So there we go. So that's why the reaction halts. Okay, cool. Right, guys, let's move on. We're near the end of the paper, and you would be doing me a humongoid favor if you hit the like. That would be super nice of you. All right, let's go through and get this last bit done. What am I doing? I'm flopping about. 9.4. Okay, we've got a question here about a metal nitrate that completely decomposes when heated. Okay, and we've been given the equation for this with the coefficients, which is always nice, and we've been given the algebraic symbol X. So we've got this unknown metal X. A 0.832 gram sample of X nitrate decomposes on heating to produce a total of 348 centimeter cubed of gas at 298 K and 100 kilopascals. Deduce the identity, I love that word, deduce the identity of metal X. The ideal gas constant R is 8.31. 6 fat bad man marks. Let's get on and work it out. So why don't you grab your calculator? You're going to need a pen. You're going to need a pad. Have a go at this, and then I'll go through with the explanation and all the details that we need. Okay, time to go through the answer. So first up, we're going to need to, well, we can appreciate here that look at the formula. We've got XNO3, right? And there's a 2 there. NO3 is 2 minus. Um, I don't know if it told us, but that means that X is definitely going to be +2 ionically. So that means that we're looking at a group 2 metal. And this is just good for our common sense check at the end to see whether it makes sense what we've calculated. All right, we've got mass. So as soon as you see mass, we can start thinking, well, I might need like mR times moles with mass at the top of my little triangle. Okay, so I might need that. We go along and we can quite easily see here we've got the ideal gas equation. Of course, you know the ideal gas equation is PV equals nRT. You should know that off by heart. If you don't know it by now, you're in big fat trouble. So learn that one off by heart. And then we need to rearrange this to find moles. We can always work out, we've been given the mass, so if we get the moles, we can work out the MR, and then we're going to be on the way to identifying metal X. Now, feel free to pause the video now. I've gone through a little bit of what you have to do and have another go at it with that information. Okay, let me go through. So in order to isolate N, because we need moles, because moles is going to allow us to use the mass to find the MR, we're going to go PV divide both sides by R, divide both sides by T, and that's going to leave us with PV over RT equals N. Now what I want to do is put the pressure. The pressure is in 100 kP. It needs to be in pascals. So we need to do our conversions. So there's a whole mark here for doing your conversions. And volume, what have they given us the volume in? They've given us the volume in centimeter, and they've given us 348 centimeter, but we actually need to convert centimeter to meters cubed. So what we're going to do, we're going to times, you could divide by a million, or if you don't want to write that out, you can just times by 1 times 10 to the minus 6, and that is going to get us into meters cubed. So we want to divide by a million to put that into meter cubed. Anyway, enough of my wiffle waffle. We know that R is always 8.31, which is beautiful, beautiful, beautiful. And we've been told we're operating at 298K, which is lovely. We don't need to convert there, guys. This is supposed to be in Kelvin. So how do you know this is supposed to be in Kelvin? What's your mental check? Oh, is it Kelvin? Is it degrees? I can't remember if I got to convert from Kelvin to degrees. Go over to the R. It says 8.31 joules per Kelvin, right? So you've got that the R is in fact is in Kelvin. So it would make sense that the temperature should also be in Kelvin. Otherwise, you can't be multiplying degrees by this if this is also in Kelvin. So here we go. Right, let's move on and smash that out. Now, here comes my issues as I flop on the calculation. Okay, so let's go through and carry this out and work out how many moles we've got. So let's convert the centimeters first of all. You might want me to break it down for you. So you can do this separately. You can bash it all in your calculator, but sometimes that doesn't work out too good. So what you might want to do is go 348 times 1 times 10 to the minus 6, and that will get you your meters cubed. You can smash this all in the calculator and get the answer. You're not getting any bonus marks for doing it this painstaking way, but that's just me being a pain in the ass. So that gives us the volume in meters cubed. We're now going to times that by 100,000 pascals, and that's going to get rid of quite a few of my zeros. So if I times these two together, and then I've got 8.31 times 298K. I'm longing this all out, but for some of you, this might help. So if you times that by that, you're going to end up with like 34.8 on the top. And then I still haven't done my 8.31 times 298K. You could stick that in brackets at the bottom. And then what are you going to get? So let's go. Oh my days, I'm getting behind the scene here. Divided by 8.31 times 298 equals, and that is going to give us 0.0, where's my point? There it is, 0.01405. Now, you could keep it all in the calc if you love it. So it goes 77058. Oh my days, check out that number. That is the moles. Now, what is that the moles of? That is the moles, folks, and I've circled them already up here, of these gases. So that is the moles of the gases, because look, it tells you this decomposes to produce a total of that gas, and it's the ideal gas equation after all. So this is not the moles of the mystery nitrate. These are the 5 moles of gases. So this is how many moles I've got. Now check the coefficient. If you had 5 moles of that, you would have 2 moles of that. Now, what you can do is just go do that, divide it by 5 times by 2, and that is going to give you the moles of your mystery nitrate. If you don't, well, essentially by dividing it by 5, you're turning it into your moles of oxygen, and then timesing it by 2, because the ratio of the oxygen to that is 1 to 2. So if that helps clear it up in your head, or you're just doing yeah, it times in by 2 over 5. You get the idea. Anywho, let's zing on. So what does this give us? Well, this is going to give us 0.00562, or you could call that 5.62 times 10 to the minus 3. Now that we have our moles of mystery nitrate, we can take it over to our triangle up here, and we can say, well, we know the mass is 0.832G, and we can do mass over moles equals the MR. So we're going to go 0.832 divided by the moles, 5.62 times 10 to the minus 3. And what is that going to give us, guys? So I'm going to go me 148.04. Okay. Yeah. So lovely, lovely, lovely. That is my MR, but that is my MR of XNO32. So that's my MR. I'm going to change color just so this bit highlights. That's my MR of X, NO3 times 2. So what I need to do now to get X, I need to do 148. Da, 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 da. We can probably forget the zero point 0.4, I reckon, but and then I want a minus NO3 times 2, and that is going to give me X. So let's work out what NO3 times 2 is. Well, that's 14, that's 16, 3 16s are 48. So what's 48 plus 14? Oh, blimey, my brain. Plus 14 is 62 times 2, that's 124, right? So I'm going to go 148. Let's screw the 0 point, whatever. Take away 124 equals 24. What group 2 element could have, so we now know that X equals 24. What group 2 element could have a mass of 24? I think you know it is going to be magnesium. I mean, essentially it's 24.3, but you get the idea, right? So we've worked that out. It's 24 is our answer. So let's go back. Oh my gosh. Okay, 9.5. Sodium reacts with aluminium and hydrogen to form solid sodium aluminum hydride. Give an equation for this reaction. Suggest why, yeah, that has a high melting point. Okay, so what is the equation for this reaction? So we're going to go sodium, still in pink, plus aluminium, plus hydrogen. What we got? 2H2. And that is going to go to NaAlH4. And that should get us a mark. That is the ugliest looking thing I've ever seen, but never mind, never mind. Now, suggest why it has a high melting point. Well, um, you're going to get strong electrostatic forces of attraction between these sodium ions and the aluminium hydride ions. So, yeah, we're going to have strong forces of attraction. So let's put that. Strong electrostatic forces of attraction between um, sodium or between oppositely charged ions. Oppositely charged ions. Um, Giant ionic lattice takes lots of energy to break. Um, Yeah, so there's lots of strong forces of electrostat. I can't. I've lost the ability to speak. So there are lots of strong electrostatic forces of attraction. Let's put the word lots there. Lots of strong. They're called ionic bonds, but lots of strong electrostatic forces of attraction. I'm going to put in brackets ionic bonds because I like to make my working all over the place. Lots of strong electrostatic forces of attraction known as ionic bonds. These forces of attraction are between oppositely charged ions. It's a giant ionic lattice, hence the lots. So it takes lots of energy to break all of those. Okay, boom, bam, bang. Right, now let's move on. Hey, we're near the end of the test. 9.6, give the equation. Okay, okay, okay. So we got phosphoric acid. It's going to react with a base. So you kind of got acid and base. What we're going to make? We're going to make sodium phosphate, right? Now, sodium da, 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 da. Surely it's just a case of that because the sodium ions swap places. So we get sodium phosphate, but then that means I need 3 sodium hydroxides. And that means how many waters are we going to make? 3OH. 3H is there. I'm going to get 3 waters. Lovely. So that was really basic. It's just your obvious neutralization reaction. You basically got acid, base, salt, and water. Lithium is an important metal used in cells to power mobile phones. In a lithium cell, lithium cobalt oxide electrode. So the lithium cobalt oxide. So lithium has the formula Li, cobalt, CO, and oxygen like this. And a lithium electrode. So that is a 2, isn't it? Because that is 3 plus. That's 1 plus. I think that's plus 1. That's plus 3, right? That's going to be minus 4. So that's going to cancel those out. Okay. So it's that. Okay. And a lithium electrode are used. Give the equation for the reaction that occurs at the positive electrode. Okay. So we're going to get lithium ion is going to go to a cobalt oxide, dioxide, and an electron, and together, oh my gosh, check out that plus. That's a big one, as the bishop said to the nun. Right, and that is going to give us lithium cobalt oxide with a minus charge. Um, or, well, yeah, actually, I should show that plus and that as minus. And that'll do the trick. Right, what's the last bit? Commercial electrochemical cells can be rechargeable or non-rechargeable. State why lithium cells can be recharged. Well, it's a reversible reaction. You can reverse the potential difference, or yeah. So reverse the potential. Um, the reaction is reversible. And there we go. That should get us all of the marks. That's the end of the test. I'm exhausted after doing that. These A-level tests take a hell of a lot out of me. If you want to see more of these tests, you best hit the like. Otherwise, I'm going to stick to doing the other ones. All right, guys. Take a lot. Take a lot. Yeah. I've lost the ability to speak. Ah, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the mark.
You're still here? It's over.